Okay, I think we've got a bit of a room full already, so I'd like to welcome everyone to this CS International Conference on the 19th of May. A first for everyone, doing it online, and so I understand we have up to 1,000 registered delegates across the 4 breakout sessions, so let's all hoping that Zoom holds out for this quite novel approach. First of all, to introduce myself, Chris Meadows from IQE PLC, part of the leadership team, but also director of CS Connected, a limited company which is the umbrella organization of compound semiconductor cluster members around or based around South Wales. Unusual times, unfortunately can't offer you the Belgian hospitality that was planned for April, but hopefully that'll be online for November, and especially the fries with mayonnaise, which I'm sure everyone is missing. But I hope everyone's settled in. You've got your own refreshments and snacks to hand, and we'll now embark on our exciting program of talks with Q&A sessions in the first ever online Compound Semiconductor International Conference. Just to give a brief outline of how the day will work, essentially there'll be a series of presentations. In this session they're all pre-recorded, but most of the speakers are with us today online and available to take questions and answers after each session. Because everyone's automatically on mute, if you'd like to ask a question, there is a facility you'll find at the bottom of the Zoom window. You can click on an area to say raise your hand. If you want to ask a question, please click on that, raise your hand, and you'll be unmuted. If one of the speakers is not available, we'll still do a Q&A, but we'll make a note of the questions that we'll forward on to the speaker to respond. In this afternoon's sessions, there are 4 themes. First of all, seeking opportunities for LEDs and lasers, enhancing the automobile, ramping volumes in the power electronics sector, and satisfying the demand for more data. And without further ado, we're going to kick straight into the first talk under the theme Seeking New Opportunities for LEDs and Lasers. And the first talk is by Akihiro Ito, staff engineer at Panasonic Factory Solutions. And Akihiro will be joined later for the Q&A session by Okita Shogo. The title of the first talk is Advanced Technology of Plasma Dicing for Gallium Arsenide VCSELs. VCSELs are now key optical sources in gigabit, Ethernet, high-speed optical area networks, data links, and sensing applications because of the advantages they offer, such as low threshold current and a small structure. During conventional dicing of VCSELs fabricated on gallium arsenide, the wafers tend to be fragile and chipping or edge cracks can easily occur. Panasonic proposes plasma dicing as a new wafer singulation method. The plasma dicing process is a technology to dice the entire wafer into chips at once. It is damage-free and increases yield. In this presentation, Panasonic explains how plasma dicing can be applied to dicing of VCSELs.
My name is Akihiro Ito. I belong to Panasonic Smart Factory Solutions company in Osaka. Today, I'd like to talk about the advanced technology of plasma dicing of gallium arsenide VCSEL. First of all, I would like to explain Panasonic Smart Factory Solutions company, to which I belong. Panasonic is divided into 7 in-house companies, and each company handles different products, such as consumer appliances, life solutions, connected solutions, automotive, industrial, etc. Panasonic Smart Factory Solutions belongs to Process Automation Business Division of the Connected Solutions Company and focuses on fields of factory automation. Panasonic Smart Factory Solutions is developing and manufacturing total solutions for the whole smart manufacturing process, such as back-end and front-end manufacturing equipment for various electronic components. In the field of compound semiconductor
Sorry, I've just stopped that sharing just because I can load it on mine full screen because Chris just shared his actual screen. So I will now share it on my screen. Just hang on a second.
Okay. Semiconductor applications. In this presentation, I will explain Panasonic plasma dicing technology applied to compound semiconductor industry. In this slide, I will explain dry etching technology.
You can just stop yours playing, Chris.
Yes, etching solution.
And I will find it on mine. There we go.
My name is Akihiro Ito. I belong to Panasonic Smart Factory Solutions company in Osaka. Today, I'd like to talk about the advanced technology of plasma dicing of gallium arsenide pixel. First of all, I would like to explain Panasonic Smart Factory Solutions company, to which I belong. Panasonic is divided into 7 in-house companies, and each company handles different products, such as consumer appliances, life solutions, connected solutions, automotive, industrial, etc. Panasonic Smart Factory Solutions belongs to process automation business division of the Connected Solutions company and focuses on fields of factory automation. Panasonic Smart Factory Solutions is developing and manufacturing total solutions for the whole smart manufacturing process, such as back-end and front-end manufacturing equipment for various electronic components. In the field of compound semiconductor devices, Panasonic supplies surface mounters as well as die and flip chip bonders in the back end. In the front end, Panasonic supplies dry etching equipment for various compound semiconductor applications. In this presentation, I will explain Panasonic plasma dicing technology applied to the compound semiconductor industry. In this slide, I will explain dry etching technology applied to compound semiconductors. Various etching solutions are shown here. Panasonic APX300 series has a lineup of 3 dry etchers. APX300S for high precision multi-spiral coil RCP processes is applied to gallium arsenide high frequency and optics, gallium nitride high frequency and optics, indium phosphide optics, silicon carbide power devices, and passivation such as silicon dioxide, etc. APX300S for high density ICP process is applied to silicon carbide vias for gallium nitride head and all silicon carbide trench processes, and APX300, which features batch processing, is for mass production. It is batch type for up to 7 wafers per batch in the case of 4 inch, 3 wafers per batch in the case of 6 inch, and is applied to LED processes. Thus, Panasonic can provide various dry etching applications for compound semiconductors based on gallium arsenide, gallium nitride, indium phosphide, silicon carbide, etc. Next, I would like to explain two trends of the pixel market and technology. As you know, pixels have a small chip size and can be driven with lower power when compared to existing lasers, and when integrated into densely packed lasers to the array structures. Pixel applications currently include laser mask, laser printer, etc., and further widespread application is expected. In addition, taking a look at the pixel market trends, market scale in 2018 is $738 million, but is expected to grow to $3.75 billion in 2024. There is, however, an issue how to respond to such market expansion. Pixel chips require dicing, but there are challenges to dice pixel chip by using conventional methods such as red or laser dicing. As shown in the left side figure, pixel chips are damaged physically and thermally. and dust gets on the chip surface. With conventional dicing technologies, pixel wafer layouts require wide dicing street widths and curve lines in order to reduce the damage. Thus, market requirements are damage-free nodes and no debris, and improving yield of power wafer by reducing the dicing street widths and curve margin. Panasonic solves these issues by providing its new dicing technology, plasma dicing, to replace these conventional dicing methods. Next, I'd like to explain principles and benefits of plasma dicing. Outline of plasma dicing is shown on the left side. Plasma dicing is a technology which processes a wafer mounted on a metal ring frame with tape as shown in this figure. Wafer is transferred into process chamber of the plasma dicer and singulated by plasma processing. As shown in lower left photo, a wafer mounted on the ring frame with tape can be singulated. The benefits of plasma dicing are shown on the right side. The plasma dicing process uses chemical reaction of gas. The first benefit is that there is no damage or chipping by using plasma dicing. The second is that high productivity and low cost of ownership are achieved. The third is that this process is dust and particle free. Finally, variant chip shape and layout as shown in lower right pictures can be achieved. This slide shows Panasonic APX300 dicer module. This photo on the left side shows APX plasma dicer's appearance. The figure on the right side is a schematic diagram of our plasma dicer's process chamber. We have optimized each elemental technology for plasma dicing. Enhanced ICP plasma source has been developed from our multi-spiral coil ICP to improve plasma density and realize high-speed silicon etching. Panasonic's patented electrostatic chuck electrode for plasma dicing makes it possible to suppress damage during plasma dicing process. The ESC has a very strong cooling capability and suppresses tape and ring damage. This process chamber can use both chlorine-based and chlorine-based etching gases. In addition, multi-layer dicing, such as silicon oxide, silicon nitride die-attach film, and silicon is possible. A silicon etching rate of 35 micrometer per minute and uniformity of plus minus 3% or less is achieved. Thus, compound semiconductor etching is possible by using Panasonic APX plasma dicer. In this slide, I would like to explain plasma dicing process flow for pixel. In this table, show gallium arsenide plasma dicing process flow incorporating photolithography technique. This process flow has 3 steps. The first step is mask patterning and is performed by photolithography processes. Photoresist is coated onto wafers mounted on metal ring frames with tape and UV exposure and development. Next, plasma dicing is carried out and finally photoresist is stripped by ashing or chemical cleaning. A feature of Panasonic APX plasma dicing equipment is that it is able to perform both plasma dicing step and ashing step inside the same chamber. Only changing the type of gas is necessary. Mask patterning with narrow street widths and curve margins on wafers mounted on ring frame is required in order to achieve this process flow. Greater than 100 micrometer depth etching without physical and heat damage on the whole wafer is needed for the plasma dicing treatment. Ashing or chemical wet cleaning are carried out for the mask stripping treatment. Panasonic can recommend photolithography and plasma dicing integration for small chip pixel devices. Next, I would like to explain photolithography on gallium arsenide wafers on metal ring frame and tape. Photo on left side shows photoresist pattern gallium arsenide wafers mounted on a ring frame with tape, and these pictures show photoresist shape on gallium arsenide wafer. Panasonic can treat wafer size from 2-inch to 8-inch. An example of high aspect ratio photoresist patterning is shown on upper row. Photoresist thickness is 14.6 micrometer. The dicing width is 6.3 micrometer, and aspect ratio of 2.3 is achieved. SEM images on bottom row show photoresist mask patterning applied to pixel. The photoresist thickness of 15.7 micrometer, dicing width of 14.8 meter, and photoresist completely covering pixel device structure is achieved. Thus, Panasonic can perform photolithography such as coating, alignment, and exposure and development with metal ring frame and tape. And this technology is applied on gallium arsenide wafers from 2-inch to 8-inch. In this slide, I would like to explain results of gallium arsenide plasma dicing. Left photo on shows plasma dicing gallium arsenide test coupon. Test coupon sample is set on center area of the ring frame, and the dummy covered with polyamide is set around the test coupon sample. As shown in this photo, there is no damage by the use of chlorine gas after dicing. The picture on the right side is a SEM image of gallium arsenide trench after plasma dicing. A vertical gallium arsenide profile was achieved, and the gallium arsenide etching rate was over 8 micrometer per minute. The etching rate uniformity of for 6-inch is plus minus 3% or less, and the selectivity of gallium arsenide and photoresist is over 22. Thus, Panasonic achieved a high gallium arsenide etching rate and high photoresist selectivity and vertical etching profile by using a chlorine-based gas etching process with a dicing tape varnish. Furthermore, I would like to show Panasonic's etching profile control by tuning plasma dicing conditions. This slide shows the result of gallium arsenide etching profile control. Firstly, I show profile control. The left side SEM image is a bowing profile, the center SEM image is a vertical profile, and the right side SEM image is a taper profile. Etching profiles can be controlled by tuning plasma dicing conditions as shown in these SEM images. Secondly, I'll show high aspect ratio gallium arsenide dicing as shown in SEM images. Etching depth of 127 micrometer, a dicing width of 16 micrometer, and aspect ratio of 8, and vertical etching profile were all achieved. Thus, very high aspect ratio process can be applied to gallium arsenide pixel plasma dicing by tuning plasma dicing condition. I'd like to show total integration of photolithography, plasma dicing, and mask stripping. Photolithography, plasma dicing, and mask stripping were performed by using 4-inch gallium arsenide wafers mounted on ring frame with tape. Before photoresist stripping, some swelling of material on the gallium arsenide pattern was evident, but after photoresist removal, Not only the photoresist but also swelling could be removed, and no debris and no dust was achieved as shown in this SEM image. These photos on the right side show 6-inch gallium arsenide wafers whose thickness is 100 micrometer after plasma dicing and photoresist removal. Thus, plasma dicing and photoresist removal process can be achieved without dicing tape damage. I would like to summarize my presentation. Panasonic can propose plasma dicing technology to singulate gallium arsenide pixel wafers. Panasonic have developed and demonstrated suitable process flows for gallium arsenide pixel wafers by using photolithography and plasma dicing. The first is photolithography technology. We can perform photolithography with metal ring frame and tape without tape damage. The second is plasma dicing technology. Panasonic APX dicer module can be applied to gallium arsenide plasma dicing by using chloride-based gases. High aspect ratio gallium arsenide dicing can be achieved. The third is mask stripping technology. Panasonic showed photoresist can be removed by chemical solutions for wafers of metal ring frame and tape. Panasonic continues to improve plasma dicing technology for gallium arsenide and intends to expand its application to other compound semiconductors, such as gallium nitride, etc. Finally, Panasonic highly appreciates the cooperation and support of EV Group and several other chemical manufacturers. If you have any follow-up with my European colleague located near Munich in Germany. Thank you very much for your attention.
And thank you, Akihiro. From Panasonic Factory Solutions. Akihiro is with us live along with his colleague Akita Shogo to take any questions, and I will kick off with one that we've received during the presentation, which was from Stephanie Backlet by text, and that is, what is the smallest size that your equipment can process and what types of mask do you need?
Thank you, Chairman. I'm Shogo Okita of Panasonic Smart Factory Solutions. In this case, we use photolithography mask. And in case of silicon singulation, we achieved minimum 5 micron dicing strength. But in case of gas plasma dicing, photoresist resist selectivity is lower than in case of silicon. So in now about 15 micrometer dicing strength is could be achieved in case of gas plasma dicing.
Okay, thank you very much. And I will open it up to any other questions. The process, as I mentioned earlier, is there should be a button saying raise hand. And if you could do that, if you've got any questions for Akita from Panasonic.
Sapphire dicing? No?
No, don't think there are any other questions. Oh, sorry, there's...
No.
No. Oh, sorry, there is one question. Can this be used for sapphire dicing? That's from Ramesh Nepali.
In now, sapphire dicing is impossible.
Okay. And any other questions before we move on? No, I think that's it. But we can take questions either by text or typing into the chat box, and we'll forward those on if there are any further questions. So thank you very much, Akita, and for your colleague for the presentation. Thank you. And moving on, our next speaker is Pars Mukesh from YOL Development, who's the business unit manager. And he poses the question, can micro LEDs and VCSELs revolutionize the solid state lighting industry? The solid state lighting industry nowadays is at a crossroads between LED industry that's has reached a critical size, but is now mature and lacks strong market dynamics, and a laser diode industry that is booming but still emerging and proliferating in terms of applications and technology landscape. In this context, two major technologies are seen as potential creators of new killer applications. These are micro LEDs and VCSELs. Whilst micro LEDs can revolutionize display applications, VCSELs have the potential to allow development of breakthrough features for smartphones, and where VCSELs have already started to make their way, micro LEDs still suffer from technology barriers. So what is needed to unlock the micro LED market, and what does the future hold for VCSELs? These are the questions that YOL will try to answer. So I'll hand over to Pars now. Thank you.
So good morning, good afternoon, everybody. Hope you're doing well. So this is Pars Mukesh, manager of solid state lighting and display activities at YOL Development. And today I will be making a presentation for this online event. The presentation will be entitled, Can Micro LEDs and VCSELs Revolutionize the Solid State Lighting Industry? A short overview. So let's get started. So before moving directly to VCSEL and micro LED topic, let's make a short introduction to solid state lighting source. So solid state lighting source aren't new technologies. In fact, they have existed since the 1960s. However, it's only in the last 25 years that they started appearing in high volume application. So laser diode found their sweet spot in the 1990s as a light source for optical transceivers used in datacom and telecom applications. Further refinement coupled with the internet's boom drove the laser diode market forward to a point where each technology has now followed its own path. I say each technology because laser diode can be basically split into two main categories of technologies. EEL for edge-emitting laser, and VCSEL for regarding vertical cavity surface emitting laser. For EEL, the demand was driven initially by the increased use of lasers in different industries, such as material processing and optical storage. And for VCSEL, it took much more time to find their strong growth drivers, but the smartphone boom created a real window of opportunity that allowed VCSEL to find their killer application in 3D sensing. Regarding LED, it's been a long time that they have been commercialized since the early 2000s. Same as for laser diode, one relay of growth was the mobile phone market, and LED were used in order to make the backlighting unit for the display. Then the second growth driver was related to LCD TV. And same principle here, the LED was used for the backlighting. And more recently, LED has penetrated the general lighting market. What has to be understood from the LED, let's say, growth is that it was a non-linear and thawed, let's say, evolution. There have been periods of recession that were followed by waves of new applications and growth, followed again by periods of oversupply that depressed the prices and so. This uneven growth resulted in a depressed environment, leading the industry to seek niche and specialized application in order to reap much more higher margins and diversify activities toward non-visible LEDs. When I say non-visible, I mean mostly ultraviolet and infrared ones. So in this context, the solid state lighting source industry is at the crossroads between an LED industry that has reached a critical size, but is now mature and lacks strong market dynamics, except potential upsides such as the micro LED ones, and we will come back on it later. And on the other side, the laser diode industry that is booming, but still emerging and proliferating in terms of application, technology, and here we'll make a specific focus on VCSELs. But before moving to those topics, I just wanted to highlight that we're just scratching the surface of light science. The visible solid-state lighting market is driven by the best established, most common functions of light. Basic lighting, as for general lighting, and backlighting, as for TV, smartphone displays, and so on. Today, visible lighting is less and less at the heart of the solid-state lighting industry. Indeed, infrared and ultraviolet lighting is experiencing much more interest. Here, good examples are related to the current situation and the use of ultraviolet light for disinfection purpose. I think you have all heard about, let's say, robots, for example, implementing UV light in order to disinfect hospital rooms and so on. For infrared, it's much more related to sensing application, and the main driver here are the smartphone, but also the automotive market segments, as we are going more and more toward, let's say, autonomous driving in this field. Now that this has been said, let's focus on the VCSEL topic. So again, VCSEL aren't new technology. They have come back on the front of the scene since few years and mostly fueled by the smartphone application. You remember back in November 2017 when Apple released the iPhone X with a new feature called Face ID? It was detecting and recognizing the smartphone owner and unlocking the phone thanks to 3 different VCSEL working together. Following this iPhone release, several smartphone manufacturers also announced that their next flagship would embed a similar features. In this context, front 3D imaging was implemented as a first step, and more recently, smartphone manufacturers have also released new product with a rear 3D sensing module for what we're going to call world-facing applications. So in this context, mobile and consumer VCSEL application generated a revenue of a little bit more than $500 million in 2018, and we expect this growth to reach more than $3 billion by 2024. Other applications are also expected to implement VCSELs in the mid to long term in different market segments, mobile and consumer for sure, but also automotive and transportation and industrial ones. But let's get back to the current hot application and try understanding how this market will further boom. As mentioned, since 2017, an increasing number of smartphones are implementing VCSEL. You can see here a kind of timeline about the different release of those smartphones implementing VCSEL. But basically, after Apple, Xiaomi and Oppo released their flagship phones with a 3D sensing feature, and even more recently, the 2 market leaders, Huawei and Samsung, began implementing those kind of VCSEL. What is of importance to understand is that on the technology side, structured light, which was used for facial recognition for the first time on high-end smartphones, implies the use of 2 different VCSEL. The first one for the fluid illuminator and the second one for the dot projector. Therefore, using these 2 light sources had a tangible cost to the 3D sensing module. Meanwhile, a face recognition module using the time-of-flight principle, TOF, was implemented by LG in early 2019. This leads to using only 1 VCSEL in the fluid illuminator and therefore a reduced cost of the 3D sensing module compared to the module using the structured light principle. And this will be key to cost decrease in order to further, let's say, increase the penetration rate of those kind of features and so of the VCSEL technology. So that was for the technology aspect. More precisely on the cost aspects, in 2017, the total VCSEL cost per smartphone was estimated between $4 and $5. The year after, it dropped to $2 and $3, between $2 and $3, evidence of a strong price decrease. As a global, let's say, forecast, we expect that by 2024, all the, let's say, VCSEL device related to proximity sensing, but also to front and rear 3D sensing module will cost around $2 per smartphone. So the idea here was mostly to mention you that yes, VCSEL is really a new relay of growth for the, let's say, solid-state lighting business, but there are still some development to be done in order to make this market a real and concrete boom. Let's move now to the second topic of this presentation, the micro-LED one. So micro-LED technology compared to VCSEL are much more emerging. There is no concrete product today. However, micro-LEDs are drawing an increasing amount of attention. Startups have raised more than $800 million by end of 2019. Apple has spent between $1.5 and $2 billion over the last 5 years, and panel makers such as Samsung, LG, AEO have also significantly increased their efforts. Patent filings are also growing exponentially, as you can see on this slide. So this is coming from our, let's say, really recent analysis made in January, February of this year. And as you can see, this is, let's say, the intellectual property activity is continuously growing. So coming back to, let's say, the recent progress and remaining roadblocks, what you have to understand is that the external quantum efficiency of blue and green micro-LED chips has more than doubled over the last 2 years. Some transfer and assembly processes are also reaching performance close to what is required to enable some micro-LED consumer application. So progress is also visible in the proliferation of prototypes presented over the last 2 years by close to 20 companies. Equipment makers have also taken notice and are starting to develop micro-LED specific tools for assembly, bonding, inspection, but also testing and repair, a really, let's say, roadblock for the development of this technology. And LED makers are also showing growing interest for this technology. So micro-LEDs, we have taken a look at the past, what is likely to happen now in the future. And here you have a tentative roadmap in order to understand where we stand and where we are going. So epitaxy and chip fabrication are no longer seen as roadblocks, but solid yield management and repair strategies must be implemented. Transfer and assembly process need to evolve from tabletop experiments to robust high-volume production tools. The proliferation of technology paths indeed creates some confusions and delays. For micro-LED companies, the first few prototypes provide strong returns in terms of experience, but maturing toward consumer-grade displays could require thousands more. Startups are entering what we're going to call the valley of death. Many might fail to raise enough money to successfully go through this more capital and resource-intensive phase. Support and partnerships with large display makers or original equipment manufacturers, either as a strategic investor or development partners, is critical. The situation is less challenging for micro displays. Many prototypes can be built from a wafer run, and setting up the supply chain is easier as a lot of steps can be outsourced. Small foundry runs are expensive, however, and non-recurring engineering costs can be much more significant. So in terms of application roadmap, smartwatches are a perfect beachhead. Low volume, small displays with high price elasticity make it possible to use larger dies and more redundancy. Additionally, Apple could push high volume manufacturing and make smartwatches a stepping stone to overcome supply chain obstacles for micro-LED. It will allow to improve the technology toward other applications. There is also a strong case for augmented reality and head-up display micro-displays where micro-LEDs could be the only technology delivering the right combination of brightness, efficiency, and form factor. For the TV market, it's much more challenging. OLEDs are progressing and might leave little room for differentiation by the time micro-LEDs are ready. For smartphone, OLED will be a mature, high-performance, cost-effective solution by the time here also micro-LED is ready. Micro-LED can't match OLED's cost. It will be very difficult. Differentiating performance and features still to be invented or required to compete. Apple still appears to be the best position to enable high-volume micro-LED smartphone. This could happen in 2 to 3 years after introduction in smartwatches, but also raises an existential question for the industry. What happens if Apple pulled the plug on micro-LEDs? So this is really a tricky question, and actually we don't have yet the answer. So that's why we have made different scenarios in terms of forecast in order to understand where this technology can lead the display panel volume market. So those are presented here. The idea is not to go into details of the different one, but much more to explain you that depending on how the micro-LED technology will evolve in the future, including the industrial, let's say, evaluation, and what will be the choice of the different players involved in this market, we might expect different future for this technology, depending also on if the TP application will work, if the smartphone application will work, and so on. So this is it for today. I would like to thank you very much for your attention, and I think that right after this presentation there will be also a session in order to, let's say, have a Q&A. So if you are ready.
Yes, thank you very much for that, Paz. We're open to questions. If you'd like to raise your hand, we can allow you to ask that right now. And the other thing I would say is that these presentations will be available online for the next 12 months. But obviously this is the only opportunity to ask a question. So fire away. Okay, I can't see any questions on this, so I'll thank you, Paz, for that.
No problem. Thank you very much.
Checking there's no lag on that. Sorry, Paz, there is a question before we go away. Could you please give us an update on long wavelength VCSELs, greater than 1300 nanometers, the development and potential market penetration timelines? There's a big question.
Yes, sorry. So yes, we'll try to answer it based on my understanding. I can't find it back on the, let's say, the network, the platform. So yes, for longer wavelength, mostly for infrared, there is a clear trend. So we see, let's say, some development toward that. The main related trends that we have, let's say, highlighted through those kind of development is first for datacom and telecom application, moving to, let's say, more and more InP material. And regarding smartphone, this is much more related to trying to much more implement the 3D sensing module within, let's say, beyond the display, after the display, in order to hide it and have no more those kind of notch design. And the second trend may be related to going to higher wavelength, not let's say 100% sure, but from what we have understood, is related also to this, let's say, world-facing application, so augmented reality application, in order to have, let's say, a much more higher distance. As you may know, facial recognition is used within 1 meter, whereas for augmented reality, you will need much more higher distance in order to make this feature work and consumer to feel comfortable using it. So I hope I have, let's say, answered it. Not sure, but in any case, you can contact me if there is, let's say, more details to be given here.
Thank you, and thanks, Paz. And there's one more question from David. Good presentation. And the question is, for microdisplays, has Facebook a dominant position? And I should say that Facebook are actually presenting, so we don't want to lose people from this room, but yeah, has Facebook a dominant position?
So here also it's a kind of tricky question. Let's say I'm not sure Facebook has a dominant position, but they have made a strong move recently toward micro LED, and let's say this deal they have concluded with Placy in terms of, let's say, being able to have a kind of exclusive license. So saying they have a dominant position might be, let's say, a little bit strong, but they have made a strong move in this field recently. And so let's wait and see to understand what is likely to happen. But we'll try to, let's say, inform you once we would have fully investigated on that one.
Okay, and sorry, one more question from Stephanie Buckley. Could you please give us an update on long wave? Oh, sorry, we've covered that, so that's fine. That's great. So that's all the questions. Thank you very much again for that, Paz from Yale Development.
Thank you, Chris.
We'll hear from Yale a bit later as well. Thank you.
Thank you.
Okay, so now to our next presentation. It's Thomas Ehrman, Director of Business Development at EVG. The title is Compound Semiconductor Integration, Wafer Bonding Towards New Dimensions. Joining different semiconductor materials can be challenging due to mismatched material properties, such as coefficient of thermal expansion or lattice structure. Wafer bonding has proven to be a viable way to combine various materials by using interlayers like polymers or metals, as well as by direct bonding. However, for compound semiconductors, the form factor is often a crucial barrier. To this end, beneficial performance characteristics relate mostly to system-level integration rather than wafer-level. Recent developments have proven that wafer-level die bonding can provide a technically and commercially very attractive solution to this challenge. It combines the benefits of two worlds in terms of flexibility and process control, whilst being scalable to high volume manufacturing. So at this point, I'll hand over to Thomas, and I believe this is pre-recorded.
Hello and good afternoon, everybody. It's a pleasure to talk today at the CS International Online Summit. My name is Thomas Luhmann. I'm heading the Business Development Department for EV Group. And today I will give you an overview about compound semiconductor integration using wafer-to-wafer bonding or variations thereof. The main reason to do wafer-to-wafer bonding for compound semiconductor and especially dies is for heterogeneous integration. First of all, however, I would like to give you a very quick dive into EV Group. EV Group was established 1980, is a family-owned business, currently with more than 1,000 employees. We are mainly active in the MEMS nanotechnology and all kinds of semiconductor markets, especially in 3D integration and advanced packaging. Headquarters is in Austria, and subsidiaries are distributed among our leading customers worldwide. Talking about heterogeneous integration sees many different flavors, mainly heterogeneous compounds, where we are actually using bond technology to stack different materials onto each other, generating new functionality and new material functionality especially. The second group is heterogeneous interfaces, where we're using hybrid bonding, for example, to stack devices or basically use it for device integration. The main obstacle here and the main hurdle for the integration is actually the wafer-to-wafer alignment, where we are using the Gemini platform, and the alignment currently achieved in such devices goes down to less than 50 nanometers. Last but not least, heterogeneous logic, that's more or less an outlook. It's not part of this presentation today. What it uses is actually to stack, for example, logic blocks or stack basically logic on top of each other by combining wafer-to-wafer bonding and lithography or deposition together. A couple of flavors for this heterogeneous integration and heterogeneous compounds. In principle, what we are trying to do and what we are doing here is to bond without any oxide layer. In this way, we can have conductive interfaces between different materials, between a base substrate that you see here in the left column, and a stacked die or a stacked wafer of a different material. Combinations which are very prominent currently in the market are, for example, silicon to lithium tantalate for a filter application, but also silicon carbide combinations where you can stack, for example, cheap polysilicon carbide and monosilicon carbide on top for power applications. But also photonic applications using gallium arsenide, indium phosphide, and other light-emitting materials, and stacking them for integration reasons on top of silicon, for example, is gaining importance in our industry. It's one of the devices where we are mainly using here an activation called COMBOND. COMBOND basically removes the oxide prior to the bonding. Another application, however, that is also getting a lot of more attraction currently, and where I would like to spend most of my time for this presentation today, is using collective die-to-wafer bonding. For collective die-to-wafer bonding, just as a short dive into the whole process, collective die-to-wafer bonding uses the help of a reconstituted carrier. So this reconstituted wafer or wafer carrier is basically silicon or glass that we are coating with an adhesive layer. On top of this adhesive layer, we are distributing the dies face up. So we can do this in an aligned way, where a die-to-wafer bonder of a third party, in this case, it's not EVG. EVG's core technology to build die-to-wafer bonders is aligning the dies on top of the wafer and then attaching them to the adhesive. So we are not doing any permanent bond, we are just lightly placing them on top of the adhesive. Then coming into a bond cluster, that's basically the whole block shown down here. in the bond cluster, we are actually doing the wafer-to-wafer alignment. So we're treating this collective carrier as an own wafer, meaning we take the collective carrier, the target wafer, we're activating them if needed, and cleaning them, flipping the top wafer, aligning them to each other, and doing the fusion bond. What is also done in the same equipment is actually the debonding. So we can do here slide or laser debonding and cleaning the surface. Overall, this transfer method of collective die-to-wafer bonding is volume proven today, and is already volume proven since several years. So the pros, clearly, we know what we are doing in this technology. The die activation and cleaning is controlled using standard wafer-to-wafer bonding technologies. The oxide is very well managed on top of the dies, and also the rework of the carrier is feasible for such processes. The cons, definitely we have, in case that a very fine alignment is needed, we have the alignment accuracy of the die-to-wafer bonder and later on also of the wafer-to-wafer bonder, which add up. It's noteworthy to say that typically a die-to-wafer bonder, there is a systematic error when you are distributing the dies. So you have a Gaussian distribution in X and Y. Actually, so in the wafer-to-wafer bonder, we can mitigate that systematic error and center this Gaussian distribution again. So we can make it, in fact, slightly better. The cost of the carrier preparation is definitely one of the drawbacks of this process technology. However, it solves a lot of integration process problems that you would have placing very small, typically very small dies in the compound semiconductor in a direct placement way. What have we done and achieved for this collective die-to-wafer bonding? So in fact, what we have achieved and what we can do also in-house is we can bond die sizes as small as 800 micrometers up to 10 by 10, so 1 centimeter. The materials that have been shown are indium phosphide, gallium arsenide, silicon, gallium nitride, and silicon carbide. Carrier sizes for the reconstituted carrier are typically 200 and 300 millimeter. For the bonding processes, we are using direct or fusion bonding. That's most of the time the starting point for compound semiconductor integration. However, what we have also proven is that it works also with metal. So for example, gold or copper adhesives such as PCB or any other permanent bond adhesive. And last but not least, also hybrid bonding. So hybrid bonding is basically a technology where about 3/4 of the surface is consisting of an oxide. And within the oxide, evenly distributed, you have copper interconnect, taking approximately 1/4 of the total wafer surface. Then in the end of the day, so you can have a fusion bond and the conductive bond in the annealing process later on. For debonding, we are typically choosing between thermal slide and lift, or laser debonding as a debonding process. Basically, all this debonding, they have small force in C. So, for example, mechanical debonding does not have that requirement. And in the end of the day, you could also lift the dies off more easily after this bond when no final annealing is done. Typically, what we see here is a bond result. What has been done was gallium arsenide, gallium nitride, where we have used copper. Its die transfer rate in this case was 100%. We also used silicon dies transferred using BCB for test reasons, also showing 100%. Or silicon oxide die transfer using direct bonding, also leading very high yield rate. Here we would see an interface which is typically hybrid bonding, meaning we have the copper interconnect islands which are embedded into oxide. Clearly the requirements for the wafer processing are very high. So what we can do in-house at EVG is less than 2 micrometer alignment accuracy, showing for this collective die-to-wafer bond process. But in the end of the day, this could be also better, but we are limited with the actual version of the die-to-wafer bonder that we do have in-house. As an outlook, all these processes that I have shown today are available in our newly established Heterogeneous Integration Competence Center. We have just launched this for the reason that we see that heterogeneous integration and many of these processes, they actually need an access or open access innovation incubator for customers, partners over the whole microelectronic supply chain. This means, for example, material suppliers, us as equipment suppliers, R&D institutes, and also customers to work together to solve the problems and shorten the development cycle and time to market for these innovative new devices. What we are providing is facility infrastructure, IT, risk reduction, process development, and process transfer in this format of the innovation integration competence center. This heterogeneous integration competence center uses different wafer bonding capabilities such as direct bonding, metal bonding, temporary bonding, and also heterogeneous collective die-to-wafer bonding for different wafer sizes from 2 to 12 inch for fully automated, but also manual semi-automated development lines. This all depends on which of the actual bond process we are using, if there is a fully automated equipment available or not. Furthermore, what we also have is then in the lithography capabilities. So also for lithography capabilities, we have a different set of alignment, resist processing development, and also further advanced resist processing, such as used for nanofill, nanospray, cover spin, black resist, for example. And also our newly established maskless exposure is available in this lab. Last but not least, I would also like to mention another very successful start of a competence center, namely for anneal photonics, where we can prove smart anneal lens molding and also layer transfer processes for adhesive in order to stack such photonics devices on top of each other. So this new photonics competence center is running now since 7 years, very successful with many different scenarios and many different use cases that have shown it from the development center into high volume production. With that, I would like to thank you for your attention and hope that you're enjoying the CS International Online Summit further on. Thank you very much and have a nice day. Thank you.
Thank you very much, Thomas. And I believe you are available for any questions.
Absolutely.
Excellent. So if there are any questions now, again, click on raise your hand and fire away. Okay, so no questions. So obviously everything absolutely clear. Again, I'll reiterate that the presentations will be available online for the next 12 months. So, and I'm guessing that if you'd like to fire any questions later, we'll catch up with Thomas as soon as we can, and maybe feedback towards the end of today. So thank you very much, Thomas, from EVG, and it's over now to Philip Green. Philip isn't available with us today, so it's a pre-recorded talk. So we won't be able to take direct questions, but if there are questions at the end, again, raise your hand and we'll make a note and make sure they go on to Philip and feed back to you. So Philip is from AngelTech, from the Chemical Products division, and his talk is on optimizing 200mm metal liftoff for small dimensions. As the LED landscape moves from traditional LED to mini and micro LED form factors, the line width dimensions and spaces are shrinking, and as a consequence, pattern definition using metal liftoff becomes more challenging. A collaboration between vendors provides an opportunity to optimize the lithography, metallization, and liftoff processes required for these small features. This is a continuation of work presented last year at CS Mantech. The current work is focusing on sub-500 nanometer dimensions. As the line width and space dimensions become smaller, the resist thickness for MLO structure becomes thinner. Optimizing the MLO structure and the metallization parameters, AngelTech has evaluated the metal thickness limits as a function of line width. So over to to Philip, and we'll have the pre-recorded talk now. Thank you.
Hi, this is Phil Green from AngelTech USA, and thank you for the opportunity to speak to you today about our work on optimizing 200mm metal liftoff for smaller dimensions. This is work that we're doing in conjunction with EMD Performance Materials from Merck and Vico PSP. Agenda of the talk, First, talk about the metal liftoff process and some results from previous studies. Talk about the challenges for 200 millimeter wafers and submicron dimensions, with a new focus on metal thickness limitations as dimensions are decreased. Now, as the metal gets thinner and thinner, there's less and less metal to carry currents, and so there's a desire to make the metal thicker to try to counter that impact. They'll show the results of our work, and then talk about some conclusions. So, the metal liftoff process is what is preferred when metals are hard to etch or inert. To carry out this process, we have the wafer, we coat it with a negative resist, we expose it, we lift and we remove away the areas where we wish the metal to be deposited, and then we actually do our metal deposition. We deposit in the areas where we want the metal, and metal is also deposited across the remaining photoresist. The final step is to lift off the photoresist, remove the unwanted metal, leaving just the metal that's desired. On the right-hand side here, we see some examples from work we presented last year at AngelTech, 0.5 micron lines and spaces with an I-line resist. In the upper figure here, we see the step 4, where we have the metal being deposited across the photoresist down inside the trenches, and we see the photoresist in the wafer surface. And after liftoff, we end up with clean lines and spaces. Now, to be able to achieve this, we really need to have a couple of features. We need to have this retrograde profile on the photoresist, and we need to have metal deposition that's at normal incidence to the wafer surface. So the metal that comes down doesn't coat the sidewalls, leaves a clean pad at the bottom without attachment, and there's clean access for the solvent to get in and remove the photoresist. So there are challenges as we get to smaller and smaller dimensions. As these line widths become smaller, typically the resist thickness has to become thinner in order to resolve these finer features. Typically, the resist thickness can't be more than 3 times the line width of the feature. Additionally, typically the photoresist needs to be at least twice as thick as the metal thickness being deposited to get the clean liftoff. So for a resist, this limits either the minimum line width that can be achieved or the cross-sectional of the metal area, the thickness. So can the aspect ratio of the resist to metal change, and can thicker metal be deposited? That's the goal of these tests. So this is key, obviously, the metallization process. Now, the deposition metal determines the shape and position of the metal within that photoresist pattern. Now, electron beam evaporation happens to have key geometrical advantages for getting normal angled incidence across a wafer. So we're using the Temescal UEFC 6100 system that's specifically designed for 200 millimeter wafers. It has a high uniformity liftoff assembly, and achieves approximately 1% non-uniformity with greater than 20% collection efficiency. It's a high throughput system with very fast pump down time, in part due to a conic chamber design that minimizes metal deposition on unwanted chamber surface areas and allows for high conductance access between chamber surfaces and the high vacuum pumps. It also holds full cassette of 25 200 millimeter wafers. The source throw distance is a key factor to minimize deposition angle incidence variation across 200 millimeter wafers, and that has been optimized in the system for these wafers. So here we show the resist thickness and the dimensions for the liftoff. Now, our tests were run here with 2 different resist thicknesses, 338 nanometer thick and 527 nanometer thick, and we worked with lines of 200 and 300 nanometers. Now here, when we have a 200 nanometer and 1-to-1 line spacing, we can see that the narrow spaces become more difficult for liftoff structures due to the retrograde profile that we want. And the common problem is it requires thinner resist to resolve, and this limits the metal thickness. Now, for the structures that we have here, we can see that we have an aspect ratio of where the metal is deposited relative to the height of the resist relative to the metal deposited, about a little over 1-to-1 here. While we have our thicker resist structure with the 200 nanometer, we have about over 2.5-to-1 height of this relative to the metal width at the bottom. Now, this work is done with a krypton fluoride sensitive resist. And we look here, we show the results that we have with a thinner resist to thickness, with dense and isolated profile features, with 50% fill, 77% fill, and 90% fill. Now, in these particular places, we have wafer cleaving to be able to get these SEM images, and there's some artifacts or defects that come about because the metal and the resist don't cleave and break in exactly the same plane or the same place all the time. So we have to ignore a couple of features that are just due to that. But if we focus in on the other areas, we can see that we have clean trapezoidal type shapes of our metal deposited on the wafer, and we have clean metal deposit on top of the resist, allowing open access for solvent to get in and do the liftoff. With the result being that after the liftoff with 200 nanometer line widths and that 338 nanometer resist at 50, 77, and 90% fill levels, we get clean liftoff across all of them. Now this, of course, required having that good photoresist structure, the retrograde profile, and normal angle of incidence deposition across the wafer. Now, if we take that same 200 nanometer line width, and we go to the 527 nanometer resist, we have a different aspect ratio of the resist. Now, in these particular cases, we had a little bit more different wafer cleaving artifacts coming in. So we've also added in calculated thicknesses of the metals and profiles that are anticipated for the geometry of the system. And they're shown on top of here to help guide your eye. So here we have a 50% metal fill in this a little over 2.5 to 1 aspect ratio, and we see we have good still trapezoidal metal profiles. However, when we get to 90% fill, we start seeing that this starts at the trapezoidal, but it starts necking down pretty fine. And this is due to the metal buildup on top of the photoresist. It has a fraction of it that's growing inward, and that's occluding deposition as it comes up. So we can see from this that if we were to increase the aspect ratio further, we wouldn't be able to increase the metal thickness anymore. This metal occlusion would begin to limit us. Now, of course, we're already getting the limit of the photoresist anyway, so there wouldn't be much path that way directly here. Now, if we increase those metal width, those lines a little bit to 300 nanometers with the same thinner resist and thicker resist, once again, adding in our calculated metal deposition profiles expected because of the wafer cleaving artifacts, we can see that on the thinner resist at 50% and 90% fill, as we saw with the 200 nanometer width, we have clean trapezoidal features. Now, in this case, on the thicker resist, 50 and 90, we still continue those trapezoidal features because although we still have that little bit of that necking in due to the metal deposit on top of the photoresist, it's a smaller fraction of that total width, so we're able to achieve an increased thickness profile. So, in conclusion, this is an ongoing study to optimize the metal liftoff process to meet shrinking device dimensions. The feature sizes have been demonstrated down to 200 nanometers, and the resist has a resolution near to 150 nanometers, so we can actually push this a little bit further than we've gone right here. Our current work investigated metal thickness to photoresist ratio, and we show that greater than 50% metal fills can be achieved when the process is optimized. And 90% metal fill has been demonstrated for 200 nanometer lines and spaces when everything is done properly. Now, we also were able to show that effective, total metal thickness has practical limits that are determined by the aspect ratio of the photoresist feature. So this has been a collaborative study with EMD and Vico, and more results on the photoresist, the solvent, liftoff process, and some critical dimensions across the wafers are collected. Were planned to be presented at CS Mantech this month, but this has been postponed to the same reason a lot of things have been postponed, and it's going to be presented at our nearest opportunity. I'd like to acknowledge the hard work and efforts of my patriots at Merck, EMD Performance Materials, and Vico PSP, and I'd like to thank you for your attention. Thank you.
Thank you very much, Phil. And yes, I'm sure the tooth honour's missing us from Mantech from last week. Thanks very much. And I would like to correct what I said earlier. Phil is actually with us. So if there are any questions, please fire away for Phil now. I thought I'd seen you online earlier, Phil. Okay, I can't see any questions cropping up at this time, but again, we can catch up if there are any, so please fire away. So thank you very much for that, Phil.
Thank you, Chris.
Excellent, thank you. So we're now moving on to the next theme, and that's enhancing the automobile. And the first presentation is from Philip Zook of Transform. Philip is Technical Marketing and NA Sales Director, VP, and the speech is about speeding onboard charging with automotive qualified gallium nitride field effect transistors. Now in production across several application markets, high voltage GaN has piqued the interest of hybrid and electric vehicle manufacturers. The technology's proven ability to increase power density within various topologies, as well as its attractive cost model, have positioned GaN to reportedly cannibalize the onboard charger market currently attributed to silicon carbide. The key to realizing this projection is the technology's reliability. In this presentation, we will learn about the importance of extended validation tests, gallium nitride's current fit rates, failure time rates, and temperature ratings, and how a deep focus on reliability enables volume production from Transform, manufacturer of the industry's first AEC Q101 gallium nitride field effect transistor. So over we go to Philip.
Hi there, my name is Philip Zook, and I'm the Vice President of Worldwide Technical Marketing and North America Sales for Transform. Today I'm going to talk to you about onboard charging and automotive qualified GaN FETs. So on our agenda for today, I'm going to give you an update on Transform, our value proposition, talk a little bit about the electric vehicle and charging pole markets, and then dive right into Transform's GaN technology and talk a little bit about a cornerstone of our reliability, and then summarize that. So today, Transform has an installed base of over 220 megawatts in the market today. And these power levels range from 30 watts all the way up to 3 to 4 kilowatts in various applications in various markets. And key factors for us is based on our great quality and reliability, the ease of design in and drivability of our technology, as well as high volume reproducibility. Recently, we released our Gen 4 technology, which is branded under SuperGaN. And this technology, as we continue to evolve our technology, we see increased performance, figure of merit, and also continue to walk down the cost curve by obviously, reducing the cost of our GaN technology, as well as reducing our complexity of our packaging. And as I stated earlier, one of the cornerstones of our technology is our quality and reliability. So we continue to drive our fit rate, our DPPM and PPM rates down. We have over 600 devices, 600,000 devices in the market today with greater than 6 billion hours of field reliability data. So continue to show great quality and reliability to all of our customers in the field. So Transform really differentiates itself by one of the few GaN suppliers in the market that owns all, is very well vertically integrated. And what I mean here is that we own the GaN FET design, we own the EPI, as well as the wafer process. So in order to give our customers the best performance and quality and reliability technology, we have the ability to adjust 3 knobs here, either the design, the EPI, or the process. Even though we don't do our own packaging, we do have a lot of patents and patent technology wrapped around our packaging, and all of our applications are done internally for our end markets. So if we look at investigate the markets for electric vehicles and charging poles, so what we see here is basically really a long-term growth opportunity in automotive, especially for gallium nitride as we continue to evolve this technology. As you can see, from 2020 through 2030, we have a CAGR of 23% increase in the electric vehicle. So this is a large market that, wide band gap, whether GaN or silicon carbide, is starting to play into this market. Now, as we look at the areas that GaN can play, as well as including the EV powertrain starting approximately in the year of 2025 and beyond, as well as the charging pole, as we drive to higher voltages with our gallium nitride technology, we see a nice CAGR of close to 20% in this market. So a lot of opportunity in the second half of 2020 for gallium nitride in the EV market, whether it's supporting infrastructure or within the vehicle itself. So where is GaN used today? So GaN today is really used in the DC to DC auxiliary inverter, or the DC to DC high voltage to low voltage batteries for various applications within the automobile, like climate control, braking, charging the 12-volt battery, and just basically drive-by-wire systems. And also the AC to DC onboard charger is another place where GaN can play today. And as I stated earlier, starting in 2025 and beyond, you're going to see GaN start playing into the electric vehicle powertrain, compete against other technologies such as IGBTs, silicon IGBTs, as well as wide bandgap silicon carbide. So if we start looking at kind of the GaN technology, so really the competitive advantage of our technology, as I stated earlier, is the ability, the ease of design in ability, as well as drivability. So our technology, and you can see in the middle here, is a low voltage MOSFET that drives a robust low voltage MOSFET that drives a high performance GaN HEMT D-mode device. So what you have here is you have decades old, reliable, and robust low voltage MOSFET driving a super fast and high performance GaN FET. And with this is that you get the ease of drivability. So what I mean here is basically all you need is a gate resistor and a ferrite bead, and away you go. So you can use off-the-shelf gate drivers such as Silicon Labs, onsemi, so on and so forth. So these are typical drivers that are already used in high voltage silicon superjunction devices. And being that we give our customers a 4-volt threshold, it's just like driving a silicon high voltage device. And on the design inability, we give, since GaN is new to power electronics, we do give some familiarity to the designers with respect to the TO packages. Now, whether it's a TO247 or a TO263, which is a D2 pack, these are packages that customers are familiar with. They're easy to heat sink, and just easy to work with. So when we talk about basically a robust gate, high noise immunity with the 4-volt threshold, gate drive margin, as well as standard gate drives. So basically it comes down to the simplicity of driving it and designing it in. So we have done a project with Delta, Fiat Chrysler, as well as the Department of Energy in a 6.6 kilowatt onboard charger. And if we look at kind of the prior art of an onboard charger, you're looking at the efficiency of somewhere in the order of 92 to 94%. And the goal here was to hit 95. But not only to hit 95, but also go from a unidirectional to a bidirectional solution. So you not only can charge the high voltage battery, but you can also use that high voltage battery to run instruments or appliances on the outside. And this resulted in a 95.1% efficiency result, bidirectional, and also decrease the size of it, because that's what GaN offers. It offers the ability to reduce the size from 16 to 40%, depending on how you look at it, and also operating at a higher frequency and a lower maximum coolant temperature. So when we actually look at the design and use our Gen 2 50 milliohm device, our 3205 and a TO247, and this is basically a 3.3 kilowatt at low line or a 6.6 kilowatt at high line. And this is charging a battery of a voltage of 250 to 450 volt DC, typically in a nominal range of 350 volts. So you've got the AC to DC bridgeless totem pole PFC, which is where GaN offers its highest value, to a design running at 150 kilohertz per phase, and then the DC to DC dual active bridge running at 300 kilohertz. So we're able to exceed the goal with respect to efficiency using these topologies with our Gen 2 GaN. But what we have now is we actually have released our Gen 3 technology. So our Gen 2 automotive qualified device was actually rated at 150 degrees C. Our Gen 3, whether it's our 35 milliohm or our 50 milliohm, is now rated at 175 degrees C. So this gives you additional headroom, and it's rated at 650 volts at 175 degrees C. Again, the nice thing about the two switch normally off solution that we have is you have a 4-volt threshold, which gives you great noise immunity, as well as plus or minus 20 volts on the gate. So it gives you lots of headroom. So a lot of headroom there, so you won't damage the device. So a lot of good things moving from the Gen 2 to the Gen 3. Increased threshold for higher noise immunity, slightly increased gate voltage maximum, also softer switching when you're driving the device, and 175 degrees Celsius. So when we talk about reliability, reliability is a cornerstone of Transform. So we've taken into account all the different aspects of the reliability of our technology, where with respect to product qualification, we've done the Q101 or JESD 47, which is basically the cookbook standard. But like other GaN suppliers, we've also done the extended beyond the cookbook. And we've done that where we increase the number of cycles, increase the number of parts, so on and so forth. But what's also important is to really understand, the lifetime or intrinsic reliability of the GaN device. We are the only GaN supplier that has reported intrinsic, or the first to report intrinsic reliability of our technology, publicly first to report that. So understanding where the GaN actually fails, understanding the activation energies, the acceleration factors, and then moving that to extrinsic reliability. So we are the first and only company to show extrinsic reliability. Extrinsic reliability is basically infant mortality. And companies use this in order to basically do their calculations for their warranty. And this is really understanding the PPM, basically the part of the curve where it's descending, and then the fit rate, which is basically the constant failure rate, and MTBF. And we continually promote our field reliability, which is currently at a defective parts per million of 3.3, a constant failure rate of 1.0, a PPM of 4, and an internal failure rate, early failure life of 0.34. So a lot of good work has been done with respect to our technology. Very reliable, understanding what the failure modes are, all the acceleration factors and activation energies, in order to supply our customers with with a great product, with a great GaN product. So, and here's an example. This is a AES, which is a company out of Europe that sells into Airbus and Boeing. So, anything that goes into the aerospace or aircraft market has to be reliable. So what you can see is there's two products, a 500 watt and a 1200 watt power supply. The 500 watt is the first passively cooled power supply, so no fan required. This continues to add additional reliability. So using GaN, keep the thermals down, heat dissipation down, and a fan is not required. So basically give a long-term reliability for the power supply, and then also the most efficient 1200 watt power supply in the market. So robust, light, and reliable, which is important for not only the aerospace, but also the automotive and any customer that we have. We want to make sure that our customers have the most reliable GaN technology in the market, and that's where we're continuing to work towards. So basically, in summary, Transform's GaN technology, our philosophy is based on basically what we consider RDDR, which is world-class or best-in-class reliability, the ease of design inability, the ease of drivability, and high-volume reproducibility. And with all four of these, our customers can be guaranteed that they're getting the best GaN technology in the market. And we continue to support, our technology continues to support the broad-based markets. So from 650 volt, we have devices that operate anywhere from 30 watts all the way up to 5 kilowatt as a single device, both JEDEC ACQ101, and also 900 volts. So we continue to drive adoption of GaN, not only by ourselves, but also with partnerships. So thank you very much for listening to my presentation, and I look forward to seeing you this fall to continue this. Thank you very much, and have a great day. Bye.
Thank you very much, Philip, and yes, look forward to seeing you 17th, 18th of November in Brussels. Philip is unable to take questions and answers, so if there are any, please feel free to either raise your hand and we'll take notes and forward on to Phil, or please type in the chat panel on the Zoom application. Thanks again, Phil from Transform. So now it's over to another look at the markets with Ezgi Dogmas from Yole. Ezgi is a technology and market analyst for compound semiconductors and specializing in the automotive sector. So looking at the automotive market, it's an important market for electronic devices. The trend towards the electrification and the automation of cars creates enormous market opportunities for compound semiconductors, including silicon carbide, gallium nitride, gallium arsenide, and indium phosphide, either for power electronic applications or sensing applications. In this presentation, Ezgi will give an understanding of Yole's look at compound semiconductor adoption by the automotive market. So over to Ezgi.
So hello everyone, my name is Ezgi and I'm working as technology and market analyst at Yole Development, and it's a pleasure for me to be here today, be part of this virtual event and share our understanding of the wide bandgap semiconductor adoption in the emerging electric and hybrid electric vehicle market. So let's start. Before starting, let me briefly introduce you the Yole group of companies. So I think many of you are familiar with us. We are based in France. So Yole Development is specialized in markets and technology research, as well as the strategy consulting. So we offer annually updated reports, but also monitor services in which we include the quarterly updated market data with direct access to the analysts. And Yole also offers financial services such as the M&A and due diligence. And our sister company, System Plus Consulting, with whom we have a great synergy, is specialized more on the tear down and reverse engineering, as well as the cost analysis on the products or systems from the various domains of the semiconductor industry. So speaking of these domains, so let's have a look at the fields of expertise covered by Yole Development. So we have three main divisions. So the first one is the photonics and sensing, in which we cover the topics of photonics, lighting, sensors, actuators, and display. And then in the second group division, we will have the semiconductor and memory computing. So here we cover the topics related to the manufacturing. So it can be equipment, packaging, substrates, but as well as the memory and the computing. And finally, in the last division, where I also belong, we have the power and wireless. So we are tackling with the topics of RF devices, compound semiconductors, and power electronics, as well as the battery. And more precisely, I'm part of the compound semiconductor activity at Yole, and we are covering the wide bandgaps, silicon carbide, gallium nitride, and also gallium arsenide and indium phosphide, as well as the emerging materials such as the gallium oxide, for example, diamond, antimonides, and engineered substrates. And today's talk will be a synergy between the compound semiconductor and the power electronic. So let's start. I think many of you are already familiar, and maybe you have electric cars already. So you see that the electric mobility is a mega trend, which has significant impacts on the power electronic industry, but also on the semiconductor industry. And what we have seen over the last years is that there has been an acceleration of the vehicle electrification, due to some singular events, I would say. So we would have the Tesla effect and Dieselgate. And also many governments have strengthened their carbon dioxide reduction targets. And there are also incentives for zero emission vehicles, such as in China, which really boosted, let's say, the development and also adoption of these electric and hybrid electric vehicles. So we can say that there has been a strong involvement from OEMs. More than $300 billion have been announced and invested in the EV/HEV market for the adoption of these vehicles in the next years. So here, let's have a look on the EV/HEV market volume forecast by Yole. So we will have the split in terms of vehicle type. So from the bottom to the top, we will have the different vehicles depending on their electrification. So the mild hybrid electric, full hybrid electric, and then stronger electrification will be more in plug-in hybrid and battery electric vehicles, and of course the fuel cell electric vehicles. And here we can say that different OEMs have different strategies in order to reach their carbon dioxide reduction target. So some are choosing the mild or full hybridization, which would give them, of course, least costly approach, and also less significant amount of changes compared to a traditional car. And when we go for the stronger electrification, such as in the case of plug-in hybrid, battery electric, or fuel cell, we have more gain in terms of carbon dioxide reduction, and also we can benefit from the governmental, for example, incentive mechanisms for these electric vehicles. And overall, we are expecting almost 25 million electric vehicles by 2024, with posting a very high growth rate, compound annual growth rate in the 2018-2024 period. So it will ask me, so what is the impact of this significant growth for us, for compound semi people? So here we see the silicon carbide. I think many of you are familiar. So silicon carbide is more adapted for the high power and high voltage applications. And when we look for the EV/HEV, the main target application is the main inverter. So today, we can say that one of the most important parameters for an electric vehicle design is the driving range. So basically, it is the kilometers, how many kilometers you can go with a full battery. And every OEM is really trying to boost this driving range. And today, we can see three main approaches which can be of great opportunity for silicon carbide. So the first approach is what Tesla did. So they have already replaced the silicon IGBT by silicon carbide in their Model 3 with 400-volt battery car. And here they can say that silicon carbide really gives the added value of higher efficiency and smaller form factor. And the trends, the second and the third approach are more related to the trends that we are seeing today. For example, the 800-volt battery in order to boost the driving range, and also to increase the voltage level of the boost converter, which will be used in the car. So in the first example, we can count the Porsche Taycan, who has a 800-volt battery. And in the second example, we will see Toyota Prius, who is using 600-volt circuitry as a boost converter. And we can say that these two high voltage platforms can be of a great opportunity for the 1200-volt silicon carbide adoption in the main inverter. And we believe that the adoption here will significantly accelerate the growth of the silicon carbide in EV/HEV market. And concerning the gallium nitride, we see it more for the low voltage but high frequency applications. So of course there will be a competition with the silicon carbide in the onboard chargers for 650-volt range. And where we see an interest for GaN is also the lower voltage applications, such as the 48 to 12 DC-DC converters. And starting from last year, actually, we have seen prototypes and key partnerships with tier ones from GaN device manufacturers such as EPC, Transform, or GaN Systems. And here you see an example from the tier one, Valeo, who is also developing GaN solutions for the 48 to 12 volt DC-DC converters for to be used in the high volume mild hybrid electric cars. And according to the company, the GaN products can really bring better performance than silicon at similar cost. So now let's have a look on the GaN and SiC power market forecasts. So on the left, you will see the power SiC market split in terms of applications. And what you see in orange, the automotive applications is really expected to dominate the silicon carbide market over the next 5 years. And when you have a look for the gallium nitride, we see that there will be in penetration in the automotive market in some small volumes, let's say, starting from next year's. And then the ramp up is expected starting from 2024 to 25. And meanwhile, it's also important to notice that the GaN volumes are rapidly expanding thanks to the consumer fast charger applications, which is also expected to dominate the GaN power market in the next 5 years. So with this slide, I would like to thank you. And these slides were extracted from various reports in the compound semi and power electronic activity. And since 2019, we have a new product called Compound Semiconductor Monitor Service, which offers quarterly updates on the compound semis, such as silicon carbide, GaN, gallium arsenide, and indium phosphide. And we will have a look at the wafer, epi wafer, and device market level. And we are also tracking the leading actors' revenues and activities in this product. So this product is offering direct access to the analysts and includes the power GaN and power SiC, which is already available, and also RF GaN and gallium arsenide starting from Q3 this year, and finally the indium phosphide and gallium arsenide for optoelectronics starting from the next year. So please let me know if you have any questions, and I would be really happy to chat and see you this year, hopefully, in conferences, and till then, stay safe.
Thank you very much, Ezgi. And yes, let's hope we can all meet up again in November. Ezgi's around for some questions, and we have one in from Lionel Lakasin, and that is there a way to improve the screen sharing? Oh, sorry, this is actually all about screen sharing on Zoom, I think. So sorry, that's not a question directly to Ezgi. Ezgi, there is a question. Have you already calculated the COVID-19 issue and whether that's going to impact any of the estimates?
Yeah, so hello everyone. So it's a really good question. Thank you for the question. I think this is something that we are all wondering right now. So since the beginning of this year, we have seen the COVID outbreak, which is quite unfortunate. But we have also seen a lockdown of several OEMs. So at some point, yeah, on silicon carbide and on also other semiconductors, we forecast some effects, some impacts for this year. So this is something that we are tracking with our semiconductor monitor service that I already spoken in my presentation. So in the next quarters, we will take more this effect into the consideration. But what I can say, I think this year, yeah, we can see some tough quarters, maybe for Q2 or Q3. But in long term, we don't really see a big effect on silicon carbide adoption. So we remain optimists. So as you see, this is a mega trend. So the EV, still be there. The carbon dioxide reduction targets are still there. And silicon carbide still has its added values. So let's say no big effect in long term, but this is to be confirmed, and this is something we will track, and I will tell you more.
Thank you, Ezgi. And another question, by the way, that was from Stefano Leone. We have a question from Abdelali Faghi, and that is, this probably isn't one you can answer directly, but maybe you can comment on it, and it's about getting rid, and how do you get rid of defects in silicon carbide transistors?
I think, yeah, from my point of view, I can give some ideas, but I know that later today there will be also some nice presentation from the silicon carbide device manufacturers. I think they can answer to this question much better than me.
Oh.
So I would say that, yeah, it is really more at the substrate level that you need to have a better quality. So if you have defects, if you start with a bad quality, let's say, substrate, your device will suffer from it. So the best quality you should have in the substrate, and then the epitaxy, of course.
Okay, thank you. And a question from Saurabh Gupta is, how do you see gallium nitride in lighting applications?
So for this one, I can say, so gallium nitride, basically, I think it's the main market. The LED, GaN on sapphire is the main market for the GaN. And here I've spoken more for the power applications. And yeah. I can say that, yeah, the GaN with its band gap, it's a physics. So it's wide band gap is really nice for the blue and also the,
okay.
Yeah, sorry,
Thanks very much for that.
Band gap, so and also the wavelength. So at some point, it's the main driving market.
Yeah, and a debate that can go on, I guess. Okay, thanks very much, Ezgi. And staying on the mobility and automotive theme, our next presentation is from Mayank Bulsara, who's VP of Global Innovation at TNSC, Taiyo Nippon Sanso Corporation. And Mayank will be talking about GaN MOCVD solutions. 5G wireless communications, electric vehicles, and advanced automotive lighting applications offer many opportunities for compound semiconductor devices, whether the application requires power diodes, high-frequency transistors, or laser chips. High-quality and high-throughput MOCVD processors are essential. TNSC was the first to develop MOCVD equipment way back in 1983 and has developed many innovations that allow for fast growth of thick, high-quality aluminium, indium, gallium nitride-based films, which in turn enable high-throughput, cost-effective MOCVD processors. This presentation will highlight key advantages of TNSC's MOCVD equipment and TNSC's full end-to-end solution for compound semiconductor manufacturers. So over to Mayank's presentation.
Thank you for joining Taiyo Nippon Sanso Corporation's presentation on gallium nitride MOCVD solutions. My name is Mayank Bulsara. I'm Vice President of Global Innovation. I'm based in the United States and part of Matheson, Taiyo Nippon Sanso Corporation's wholly owned subsidiary in the United States. Taiyo Nippon Sanso Corporation, TNSC, was founded in 1910. We're celebrating our 110-year anniversary this year. Headquartered in Japan, TNSC now has a global presence, including Matheson, its US subsidiary, and a recently established European subsidiary, Nippon Gases. As part of TNSC's commitment to innovation and support of its gas customers, TNSC was the first to develop MOCVD equipment in 1983. TNSC has been providing R&D and high-volume production MOCVD systems for almost 40 years. In combination with TNSC's other product portfolio, TNSC can provide full end-to-end solutions for MOCVD applications. MOCVD equipment, supporting equipment for cleaning of quartz and graphite components, specialty gas sources, including ammonia and silane, and gas purification and abatement systems for highest purity delivery of sources and safe and efficient handling of gas byproducts. All of TNSC's MOCVD solutions can be found on our website, www.mocvd.jp. Gallium nitride was first applied for blue and green LED applications, and since that time, it has gained importance for other applications as well. Gallium nitride will be used for high-frequency electronics in 5G communications networks. Gallium nitride vertical power diodes will find application in electric vehicles where high currents and voltages need to be switched. and data centers where power management will be very important. Gallium nitride lasers will find their place in headlights for most advanced automobiles. And all these applications require high quality films, some very thick device layers, and all require high throughput processes. TNSC MOCVD systems have several advantages. I highlight two here: atmospheric pressure processing and an injection nozzle design that limits parasitic reactions. These combined allow for the high growth rate of high quality films. TNSC has established high growth rate processes for gallium nitride on its UR25K and UR26K platforms, and high aluminum content and algan layers in its SR4000 HT platform. At a prototype phase, TNSC is developing a hydride VPE system for deposition of thick gallium nitride films with growth rates greater than 350 microns an hour. TNSC has been making MOCVD systems since 1983. Our first gallium nitride systems were introduced in the mid-1990s, and I highlight three of our main platforms here: the SR4000 HT, the UR25K, and the UR26K. The SR4000 HT has high temperature capability and process films up to 1350 degrees C. Can process one 4-inch wafer or three 2-inch wafers, and is ideally suited for UV LED applications, power diodes, and lasers. The UR25K is a production system that can handle multiple 4-inch wafers or 6-inch wafers, and an excellent solution for gallium nitride vertical power diodes and lasers. The UR26K can be configured for 8-inch wafer processing or 6-inch wafer processing, and has been established for gallium nitride on silicon lateral power devices. One of the advantages of high pressure processing is the ability to minimize carbon impurities in gallium nitride power diodes. Carbon impurities limit the performance of gallium nitride devices, and under normal circumstances, the 5:3 ratio can be increased to reduce carbon incorporation. TNSC's high temperature and high pressure capabilities allow for greater degree of freedom to reduce the carbon incorporation even further, allowing for greater potential for gallium nitride power diodes. In addition to the film processing, dry cleaning solutions for MOCVD components has gained prominence because dry cleaning of carriers and components allows for low temperature cleaning processes and the elimination of wet chemical processes which could erode the material quality. TNSC has a DEX 526 system which has demonstrated the ability to move gallium nitride deposits on graphite and quartz components for single wafer carriers or multi-wafer carrier configurations. TNSC has demonstrated you can remove up to 50 microns of gallium nitride deposition in 4 hours or less at process temperatures which are much lower than traditional bake ovens, but very standard gases, chlorine and nitrogen. This slide shows examples of MOCVD components, graphite and boron nitride in these examples, which were coated with gallium nitride films, and after processing were completely clean, can be used for application in MOCVD processes. To summarize, TNSC compound semiconductor capabilities are total. They can provide solutions for gallium nitride on silicon with the UR26K, gallium nitride on gallium nitride vertical power devices and lasers with the UR25K, and high aluminum content aluminum gallium nitride alloys which are used for vertical power and UV LED applications, the SR4000 HT. TNSC is continuing to innovate and develop technologies like hydride VPE, for deposition of thick gallium nitride drift layers, and can provide sources, as mentioned, ammonia, silane, chlorine, and arsine and phosphine for even other MOCVD processes. TNSC's gas purifier technology is well established. The NanoCam and PureMate solutions are widely available. And for gas abatement, TNSC offers the UltimaZorb and Hercules platforms. Thank you very much for your time and consideration. And please feel free to contact me. My email address is mbulsara@mathesongas.com. Thank you.
Thank you very much, Mayank. And again, you're available now for any questions. So if anyone does have any questions for Mayank, please either raise your virtual hand or type into the chat box on the Zoom application. I think you may have got away lightly, Mayank. but again, type in any questions into the chat at any point during the presentations, and we'll make sure we pass those on. Okay, so thank you very much, Mayank.
Thank you.
Thank you.
Bye-bye.
Okay, bye-bye. And now we're moving on to the next theme, which is ramping volumes in the power electronics sector. And our first speaker in this section is John Palmore, who's CTO for Wolfspeed, part of the Cree Group. John's presentation is driving the revolution in wide bandgap devices. Historically, silicon-based power semiconductors have served as the backbone of power systems, but wider bandgap devices are changing all of this. As the market for these devices grows, it's important to understand what drives the commercial market to use wide bandgap devices versus the more established silicon technologies. Wide bandgap materials deliver results that aren't possible with silicon in the areas of power and RF. These improvements can have a significant impact on reducing overall electricity consumption worldwide, and in particular, silicon carbide is enabling electric vehicles with longer ranges and lower cost. This adoption is driving a very rapid expansion for the silicon carbide market and its associated supply chains. So over now to John's presentation.
Hi there, my name is John Palmer. I'm CTO for Wolfspeed, a Cree company and one of Cree's original co-founders some 32 years ago. So I want to thank the organizers of CS International for letting me speak. Today I'm going to mostly focus on the role of silicon carbide in battery electric vehicles and how we're getting ready for that. So battery electric vehicles have been targeted for rapid growth in the automotive market. They help the automotive OEMs meet strict emissions standard targets because they're zero emission, and that helps offset the use of traditional internal combustion and hybrid electric vehicles. So in the last few years, over $300 billion of investment in EVs has been announced, with virtually every auto company being involved. Why are silicon carbide power MOSFETs being rapidly adopted? Well, silicon carbide is already pretty well established on the onboard chargers, particularly for the size benefit that it brings and efficiency, and it's gaining traction in offboard chargers at this point. And then the next wave is for the improved range and or cost for BEVs versus the current silicon IGBT solution in the inverter itself. So the drivetrain inverter is the next big phase of adoption and will drive a lot of growth. The battery electric vehicle market expansion will be aided by what silicon carbide brings to it, because some of the big fears about battery electric vehicles are about the range anxiety, upfront costs, and charge time. And we can address all of those. We have smaller, lighter, faster, more efficient onboard chargers. In the inverter application, we can offer 5 to 10% improvement in efficiency, which means you can go 5 to 10% further on a charge in range, or you can take 5 to 10% of your battery pack out of play, which is the most expensive part of the vehicle. And then for offboard charging, we are enabling
faster, more economical charger times for superchargers. So to show the change that has happened over the years, we were out talking to automotive companies back in 2017, asking the question, do you plan to use silicon carbide in your inverter by 2025? In 2017, the answer from most was no. The fear was about reliability, cost, and a number of issues. But there was one notable automotive company that was saying yes. And as most of us know today, that was Tesla. And Tesla is now shipping silicon carbide in its inverter for the Model 3, the Model S, and the Model X. That gained a lot of attention. So a year later, as companies were looking at the benefits that silicon carbide could bring, now a lot of companies were saying yes. They think they probably will. So a number were saying yes, and some were like probably, and not nearly as many saying no. That was a year. Another year, again, building on the success of Tesla and others, now, and companies doing development work and looking at the benefits, now a majority of the automotive companies say yes, they do plan to put silicon carbide in the inverter, with a large percentage also saying probably, and actually not many saying no. So this is a very rapid change over the course of a few years, and that's very exciting for us. So why is that change coming about? Well, it comes down to efficiency. So what we're showing here is the losses of a classic silicon IGBT, say 100% of the losses here, as a function of current in the inverter application. So this first chart I'm showing you here on the right is for an 800 volt bus. And you can see at full load, 500 amps, silicon carbide offers a 50% reduction in losses at full load. But a car spends very little time at full load, and most of the time, cruising down the highway, you're in this low power region. You're not accelerating, you're just kind of keeping the car going. And that would be in the range of more than 70% reduction in losses, or right around 70% reduction in losses. And that reduction in losses is what allows the 5 to 10% improvement in range. Now, at 400 volts, now we're comparing against a 650 volt silicon carbide versus a 650 volt IGBT. At full load, you can see the advantage is not quite as big at 400 volt bus, but it's still a 40% reduction over the IGBTs at full load. But again, the car spends most of the time at low load. And here, again, we're seeing about a 65% improvement or 65% reduction in switching losses. That has gotten a lot of people excited about what that can do for their range and their cost. And so based on the strength of some of those results that I showed you from Delphi, Cree and Delphi announced 6 months ago or something like that, that we had won a major European automotive manufacturer who is launching a car with an 800 volt inverter. Delphi is making that inverter based on our silicon carbide and silicon carbide chips. And that car model is scheduled to go into production in 2022. So that will require a large ramp up in capacity. So what are the biggest concerns from all of the automotive OEMs that we talked to? The number one concern is silicon carbide wafer and fab capacity. Because as we get into these automotive quantities, particularly for the inverter, which takes a lot of amps, capacity demands for silicon carbide is essentially a quantum leap. It's a very large increase from where the market is today. So I'm going to tell you what Cree is doing about that. So we sell silicon carbide wafers and epi to the merchant market, as well as using them ourselves in our manufacturing. And this shows within our existing materials building how we've ramped since 2017. So you can see we're capable of 4 or 5x now of materials capability, output that we were in 2017. And the very large majority of this is 150 millimeter or 6-inch wafers. We plan to continue ramping up that capacity and fully outfitting this factory as a dedicated materials factory. But it won't stop there. On that same campus, we have a shell of a building that will be our next materials factory, which will allow us to continue that curve going up much, much more to meet this oncoming demand. So we not only use the material ourselves, we are the largest supplier of silicon carbide wafers to other people in the industry. And we've been winning with some key deals announced, long-term agreements with ST Micro, 500 million, 500 plus, Infineon, 100 plus million, onsemi, 85 million, and a fourth unnamed customer, 85 million. In fact, between these that were publicly announced and other long-term agreements that we've had, we now have about a $1 billion backlog in contract wins that are through these multi-year long-term supply agreements. So all of these companies are going after both the automotive and industrial markets, and they're trying to secure their supply now so they can have confidence as they go in to these markets that they can supply the material. So in terms of wafer fab, we are also expanding a lot. Also about a 30x increase from 2017 to 2024, 25 range. So where we have been manufacturing devices is on the left here, the RTP fab in North Carolina, which is a fairly small fab. That continues to run, and then we are converting another fab we have in North Carolina to be able to do power MOSFETs, and that fab is now coming up, and it will all be devoted to 150 millimeter, both of these fabs at this point. But these are fairly manual, bay and chase, kind of old style fabs. So at the same time, what we're doing is we're building a brand new fab that will really be a state-of-the-art fab in Mohawk Valley near Utica, New York. And this will be a large ballroom style fab that's much more highly automated, really, the most modern manufacturing that we can get, and a very large jump in scale. We are building this to be a 200 millimeter fab. We will likely bring it up on 150 millimeter, but we will convert it to 200 millimeter wafers, 8-inch wafers, as soon as we are ready to do that. And that will represent a very large increase. Addressing costs, one thing, obviously, these high volume fabs get you is a reduction in cost, and you have to remember that in both materials manufacturing, for the substrates and the epi, and the fab, we are very early in the cycles of learning compared to silicon. So this increased volume and increased learning is going to lend quite a bit to cost reduction as we increase our cycles of learning. So further declines in costs will be coming along with this expansion. A little bit more about the fab in Mohawk Valley. So we're investing $720 million over 5 years. Again, it'll be a highly automated fab facility in Marcy, New York, with 110,000 square feet. And the total fab facility, that's square feet of clean room, total fab facility is 350,000 square feet. And as I said, it will be 200 millimeter capable. So construction has started on that. Here you can see we're trenching for conduit and piping, and we are now pouring concrete. So here's some of the work on the foundation. So things are moving ahead despite the challenging COVID environment that we have. Things are forging ahead on the building of this facility. So we're excited to see that come online. So to summarize, silicon carbide will help EVs win, and its MOSFETs are being rapidly adopted into battery electric applications. We offer improved range and/or cost for BEVs versus silicon IGBT solution. already well established in onboard chargers, and we're gaining traction in offboard chargers, enabling much smaller systems and faster charging times. And the inverter in the drive chain will be the next big phase of adoption, and it's a lot of silicon carbide that will require. The BEV market will see a rapid expansion in the market due to the benefits we bring through smaller, lighter, and more efficient chargers, longer range for a given battery charge from 5 to 10% again in inverter efficiency improvement, and faster, more economical charging times. So to meet this demand, Wolfspeed is investing very heavily to be ready for this automotive market. So with that, I thank you for your time and appreciate again the organizers for inviting me. Goodbye.
Thank you very much, John. John Palmer, Chief Technology Officer for Wolfspeed, part of the Cree Group. And we have one question for you, John. What are the chief advantages of silicon carbide over gallium nitride in the 650 volt market? And that's from Tim Smith. I think you're still on mute, John.
So we actually haven't seen a lot of comparisons with 650 volt GaN. The story about GaN is it's silicon carbide performance at silicon prices, but so far, from what I've seen, silicon carbide is actually less expensive than GaN, just doing comparable pricing, you know, out of distributor pricing, DigiKey, et cetera. So gallium nitride, you know, you remember these electric drives are relatively low frequency. These are in the range of 10 or 15 kilohertz. So the switching losses are actually not the dominant advantage. And typically where we see GaN more competitive is in the higher frequency applications. So a DC to DC converter might be up at 100 or 200 kilohertz, where GaN might have an advantage at 10 to 15. I don't see a big advantage of GaN.
I think you've also answered the second question, which is from Stefano Leone, which is Wolfspeed is also a leader in gallium nitride technology. So how do you see GaN competing in electric vehicles? But I think you pretty much covered that in the last.
Well, yeah, I mean, you know, we are a gallium nitride company. We obviously make a lot of gallium nitride LEDs, and also are very heavily invested in gallium nitride for RF applications. We think for RF, power RF, gallium nitride is definitely the best technology. We do not pursue gallium nitride for power because we've got silicon carbide and we know where costs are going and performance. And we think silicon carbide is the better choice for power applications, at least 600 volts and higher.
Okay, and we have Prava Sana asking, what are the critical reliability challenges for silicon carbide MOSFETs at the moment?
Reliability really is not a concern anymore. You know, we wouldn't be getting all this interest from automotive if reliability was a concern. I think it's really moved more from a reliability discussion to a automotive quality discussion. The fundamental technology has been proven time and time again to be very, very reliable. The question is, you know, how many infant mortalities do you have? How do you get parts, not parts per million failures, but parts per billion? That's a quality discussion, not a reliability discussion, and has to do with how well you manage your screening, et cetera. That's really what most of the discussion is about. It's not really a reliability challenge. It's a quality challenge.
Right, thank you. Thanks very much for that, John. Right, no more questions now, although we're extending this and it leads nicely into the next presentation, which is from Richard Eden of Omdia. Richard will be analyzing the GaN versus silicon carbide story. So Richard's talk is the silicon carbide and GaN power semiconductor market, forecasts and drivers. This presentation will share knowledge and key findings from the latest Omdia report on silicon carbide and gallium nitride power semiconductors. It will present the likely key applications, pricing trends, the supplier landscape, and the latest 10-year forecast by application for both technologies. The silicon carbide and gallium nitride wafer substrate supply chain will also be discussed. And finally, Richard will try to answer that old chestnut. Our Cree Wolf Speed's expansion plans announced in May 2019 intended to monopolize the silicon carbide market. So leading on nicely from the last presentation. Over to you, Richard.
Hello, I'm Richard Eden, a Senior Principal Analyst at Omdia. Today I'll be talking to you about the SiC and GaN power semiconductor market, its forecasts and trends. First of all, I would like to introduce Omdia. In August 2019, the ownership of most of the technology, media and telecommunications business of IHS Markit, where I used to work, was transferred to Informa plc. In January 2020, we became Omdia. Omdia is just one of over 100 business-to-business brands within Informa. We help clients grow through strategic advice, insights, and deep knowledge of their markets. Here are the contents of today's talk. The GaN market again includes GaN system ICs. These cover both GaN transistors co-packaged with silicon driver ICs and monolithic GaN transistors with driver ICs formed on a single chip. This slide describes the methodology used to compile the 2020 silicon carbide and gallium nitride power semiconductor report. I want to highlight the thoroughness of conducting over 40 new interviews in late 2019. Also, please note the report is based on collected opinions and modeled to device adoption rates. It's not based on bottom-up calculations or reported supplier data. Here are the manufacturers of silicon carbide power semiconductors. There were two important acquisitions among the SiC wafer suppliers in 2019. ST Microelectronics bought Norstel Sweden, and SK Siltron bought DuPont's SiC wafer business, formerly known as Dow Chemicals. The final change worth mentioning is that Global Power Technologies Group changed its name to SemiQ in late 2019. Here are the developers of gallium nitride power semiconductors. The new entrants to the market were Power Integrations, which is already in mass production, Next Gen Power Systems, and Tokore Technology. ST Microelectronics acquired a majority shareholding in Hexagon earlier this year. Here is a list of selected GaN foundry service providers. The availability of foundries that can fabricate devices should stimulate the growth of a fabless GaN sector. The key trend is the increasing presence of major silicon power semiconductor companies getting involved with wide bandgap materials. And as the market matures, supplier consolidation increases. After 2 years of constrained supply of SiC wafers, 2019 saw better availability, so device average sales prices fell faster than in 2018. As the GaN market becomes established, competition between suppliers and increased production capacity are driving average prices down. The SiC wafer supply market is slowly opening up, but wafer prices are not falling fast enough. There's not enough competition with the market leader. Silicon carbide material costs remain too high. More wafer production capacity is needed if supply is to match the forecasted demand. Many GaN device manufacturers and foundry service providers carry out in-house epitaxy on silicon wafers. This means that relatively few third-party GaN epi wafers. Overall, the epi wafer quality is getting better, but there's still scope for further improvement. This is the forecast for silicon carbide power semiconductors for different application sectors. The total market forecast is lower than it was last year, because demand for almost all applications has slowed since 2018. The equipment forecasts used here all date from 2019, so do not take into account the COVID-19 pandemic. Growth in the silicon carbide market slows a bit from 2016 onwards due to the cannibalization of low-cost gallium nitride replacements. This is the forecast for gallium nitride power semiconductors for the same application sectors. The use of GaN devices in power supply applications has increased due to the use of GaN system ICs. They are gaining popularity in power adapters and chargers for mobile phones, tablets, and notebook PCs. Suppliers introduce products to the market earlier than anticipated and increasingly high volumes. The large other applications section contains things like wireless charging, automotive LiDAR, medical systems, and other things which have yet to be invented. This is the combined forecast for both SiC and GaN power semiconductors by product. The use of full SiC power modules in hybrid and electric vehicles from 2024 to 2026 causes a significant uplift to the overall market. As time passes, the forecast has reduced slightly due to slower than expected adoption. The key changes since last year is that demand for almost all applications slowed since 2018. This is particularly true for the automotive sector. As SiC use in hybrid and electric vehicles is significant to the overall SiC and GaN market, this affects the shape of the forecast going forward. I was asked to investigate the question, are Cree's expansion plans announced in May 2019 intended to monopolize the SiC market? The clear consensus was no, Cree will not monopolize the SiC market. It's only trying to lead the market, not monopolize it. Adoption has now started in actual projects in several applications for both SiC and GaN, not just PFC power supplies and PV inverters. The hybrid and electric market is increasing all the time using silicon IGBTs. Silicon carbide usage in this sector will grow between 2023 to 2027 as silicon carbide starts to appear more widely in powertrain inverters. Hybrid and electric vehicles will become the biggest market for silicon carbide. In conclusion, silicon carbide turned a corner in 2016 and gallium nitride is sure to follow. Both markets anticipate growth to accelerate, especially from 2022 onwards. This is me, my immediate colleague in Arizona, and our manager, who is also based in Arizona. Thank you very much.
Thank you very much, Richard. And I know you're available for questions right now. So if there are any questions for Richard, please raise your virtual hand or write in the chat box in the Zoom application. I can't see anything coming in, but I know Richard, it ties in very neatly with the previous talk. So thank you for that. Okay, that's great. Thank you very much, Richard. And now we're moving over to Gerald DeBoy, Senior Principal Power Discretes and Systems Engineering at Infineon. And Gerald will be presenting a talk entitled Driving the Adoption of Cool-GaN Technology. With the commercial availability of gallium nitride-based power devices, the positioning of the technology versus next best silicon or silicon carbide-based alternatives is a hot topic in the industry. Reliability aspects and system benefits are key issues driving the adoption of the technology. Gerald will discuss a number of use cases such as hyperscale data center and high-density telecom power supplies to outline the decision factors in favor of gallium nitride-based solutions. In this presentation, Gerald will compare performance indicators towards the next best alternatives and will address both power supply engineers as well as market analysts and trend scouts. So over to the presentation by Gerald. Thank you.
It's my pleasure to introduce Infineon's Coolgarn technology. Coolgarn is a lateral technology based on gallium nitride. It's an E-mode HEMT. We are seeing value for our Coolgarn technology both in low power, in applications such as charger and adapter, in the medium power segment for television and all-in-one PCs, and in the high power segment here specifically in telecom and server designs. My talk today will focus on the high power segment, where I will talk about server and telecom. When we look into server designs, the first point is to choose the right architecture. Modern hyperscale data center architectures such as Open Compute 3.0 took out the uninterruptible power supply, helping to save 4 percentage points in operational expenditure in the electricity bill. The backup power is now part of the rack. Furthermore, the power supply has moved away from the motherboard and is now part of the rack infrastructure, delivering 48 volt or 12 volt directly to the motherboard. When we are optimizing such a topology towards efficiency, typically in 3 kilowatt power supply units and an N+1 redundancy, we need a bridgeless PSC topology. We need to get rid of the bridge rectifier. Typically, we're using a totem pole configuration, one high frequency leg where gallium nitride devices are used, one low frequency leg where silicon superjunction devices will be used. Typically, such an architecture uses an LLC, especially for 12 volt output where we talk about quite high output currents. We need a so-called matrix transformer structure where we are integrating several cores into one magnetic structure. As you can see from this comparison, where we are simulating entire designs with a technique called Pareto font, which has first been introduced by Professor Kohler from ETH Zurich, you can see that gallium nitride-based designs are always ahead of silicon-based designs by typically 0.3%. Now 0.3% may not sound too much, but when you are striving towards 98% efficiency, every 1/10 of a percentage point counts. And achieving 0.3% by taking the right power switch technology is a major step forward. These designs are typically at 30 to 40 watt per cubic inch. Now servers become ever more power hungry. Therefore, power density comes back to the game. And here gallium nitride can be used to strive even towards 100 watt per cubic inch. So doubling the power density from today's state of the art by more than a factor 2. If we strive towards 100 watt per cubic inch, we need to stack boards. We need to take a look where we can kind of hide the DC link capacitors, like here in this case, lying them below stacked boards. We're using matrix transformers, planar magnetics, combining all the 4 cores into one magnetic structure, leaving only one path for the magnetic power flow, and basically forcing all the secondary side windings to be equal. This helps to eliminate any circulating current on the secondary side and to further enhance the efficiency. We're using a combined control scheme of LLC and boundary mode, bringing together these 2 control concepts in a concept which we called hybrid control. Last but not least, cost is always important. As we take out the uninterruptible power supply, bringing the battery into the rack, we're saving 4% of the electricity bill. We optimize the power supply from 92-93% towards 96 to 97%, another 4 percentage point. With a power use effectiveness of 1.3, saving 8% per rack, we get another additional 3% out of the cooling, bringing us in total to more than 10% savings, combining the right architecture, the right power supply topology with gallium nitride. The overall total cost of ownership, when we calculate, for example, a 7 years use case, gallium nitride is a reliable technology. We're doing a lot in terms of choosing the right concept, predicting the lifetime in applications like server and telecom. You can see here in comparison, blue designs based on silicon, orange designs based on gallium nitride, that they are overall very close in terms of total cost of ownership. And if we move beyond 45 to 50 watt per cubic inch, gallium nitride is already winning. One example from our customers, in this case, one of our telecom customers took gallium nitride into a power supply achieving 98% efficiency. If you compare this with legacy power supplies of 92% efficiency, you are getting tremendous savings in terms of electricity bill, which is far higher than the additional cost of the power supply. So overall, a very nice use case with a very short amortization time. Summing up my talk, the value of gallium nitride is fully released in combination with the right power architecture, the right topology, and the right control scheme. Gallium nitride is competing with silicon on the one hand side. Silicon would have typically more complex control schemes, and it's competing with silicon carbide MOSFETs, specifically in the totem pole at relatively low switching frequencies, like 40 to 60 kilohertz. In our eyes, gallium nitride is already better at these low frequencies, but revealing the full potential at very high switching frequencies and being instrumental if you want to drive switching frequency towards 400 kilohertz plus up to 1 megahertz. As I showed on the last two slides, there is a positive net effect on the total cost of ownership. So gallium nitride is already affordable now and will transform the market and creating a bunch of value in the high power segment. Thank you very much for your attention.
Thank you very much, Gerald. And Gerald is with us if you'd like to answer, to ask some questions. Again, raising a virtual hand or just typing into the chat box. We can fire questions at Gerald. No, I think that's everything. So thank you very much, Gerald of Infineon, for your presentation. And staying on a very similar note now, we move over to Mark Deneen, Technical Marketing Manager at Oxford Instruments. Mark's talk is entitled Advanced Plasma Processing Solutions Enabling the Cost Down per Wafer and Critical Device Performance Required to Accelerate the High-Value Manufacturing of Gallium Nitride and Silicon Carbide Power Devices. Gallium nitride and silicon carbide power devices are now commercially available, but the next generation will involve more complex structures, and for wide-scale adoption, technical challenges must be overcome and costs reduced. By focused development and leveraging over 37 years of compound semiconductor technology knowledge, Oxford Instruments plasma technology has produced advanced remote plasma-enhanced atomic layer deposition and plasma etch solutions that give superior device performance and cost down per wafer. Remote PE ALD is used to create dense high-K films for gate dielectric and passivation, whilst atomic layer etching, ALE, introduces a new paradigm in etch depth accuracy, essential for recessed gallium nitride high electron mobility transistors. Working closely with its customers, Oxford Instruments ensures that they have the tools to get the most out of their devices. So over to you, Mark.
Hello and welcome to today's presentation from Oxford Instruments Plasma Technology entitled Advanced Plasma Processing Solutions enabling cost down per wafer. I am Dr. Mark Deneen. I am Technical Marketing Manager at Oxford Instruments. The eagle-eyed among you will have noticed I am not Fraser Anderson. He sends his apologies. He couldn't be here today. So I hope you'll find the presentation interesting. Please ask any questions at the end. I'll be happy to answer anything I can. Okay. First of all, a little about Oxford Instruments itself, where plasma technology is part of the Oxford Instruments Group. We're a large company with a global customer base. We were the first commercial spin-out from Oxford University, and our founders made the first commercial available superconducting magnet. And since then, we've been continuously innovating and creating new technology that our customers demand. As I said, we are a global company with labs in the UK and also in Taiwan at ITRI, and a global service organization enable our customers to get the service they require. So plasma technology itself has been almost like a founder member of the CS community. I myself have been working on compound semiconductors for over 20 years. First of all, gallium nitride, then indium phosphide, gallium arsenide, all the major compound semiconductor materials. So we've got years of expertise within the company, and we use that in the UK lab. We've got 45 technical experts, 27 lab systems with a multitude of measurement tools, and this enables us to ensure that our solutions, by which I mean the combination of the correct hardware, but also the knowledge, the process knowledge, combined to create the solutions, are the best that we can achieve. We also collaborate globally. We have a worldwide network of collaborations, both with universities, but also customers, commercial customers. And through this, we get to really understand what our customers require now and going out into the future. So we focus on a select few markets around the compound semiconductor space: VCSELs, micro-LEDs, edge-emitting lasers, augmented reality, gallium nitride HEMTs, silicon carbide power devices. And we look at how we can improve material quality, possibly post substrate improvement, and then also really focus down on what our customers require for their device. So it's the performance that is key. It's not what we can. It is what we can achieve with the plasma, but it's definitely what our customers get out of it with their devices. And we look at yield, improving uniformity, getting the most out of each and every wafer. So the compound semiconductor production market is a fantastic place at the moment. I've watched it mature and grow, and now it really is penetrating the mainstream. The compound semiconductor materials can achieve performance that mainstream silicon just cannot, and it is really driving the growth within the industry. As I said, for example, fast chargers based on gallium nitride devices, electric vehicles using silicon carbide technology, facial recognition through 3D sensors, VCSEL-based gallium arsenide, AlGaAs-based materials, and so on and so on. So the world market drivers are really dependent on the performance that compound semiconductor materials can achieve. And we have key processes within those particular devices. So we've really focused down on what we can do to improve those devices, to make sure that they are the best, give the highest yield for the wafers. And with our years and years of expertise, we are really able to deliver performance that our customers require. Say, for example, VCSELs. VCSEL technology expanded massively in recent years with the uptake of facial recognition for mobile phones. Here we have a very simplified VCSEL process flow, and plasma etching is a definite requirement throughout the VCSEL manufacturing flow. from the Mesa pattern, making sure that the mask used for the Mesa etch is correct in profile and sidewall smoothness, and then the Mesa etch itself, and then passivation of that surface and any anti-reflective coatings required to get the most light out of your device. Like I said, we really focused on the solutions for this market, and we developed an extremely low footing process. We know that with the complex structure of the VCSEL device, having a very low foot means that you can get better performance because you're not impinging on other layers throughout at the bottom of the feature. And we can achieve this both on a vertical profile and also on a sloped profile. So we really focused down on this, and we've achieved some very good results. I mentioned uniformity, so it's no good having that profile just in one place. This is uniform across the whole wafer. So as wafers now move to 6-inch, we are able to achieve plus or minus 3% across the whole wafer, which means that our customers can make devices across the whole wafer. Looking towards the next generation of devices, there's some talk about going to more tightly packed VCSELs, allows you to get more power from a packly dense array, and this also requires new etch processes. So we developed new etch processes to fit the device structure going forward. Now on to the gallium nitride that I mentioned. The E-mode device is the desired configuration going forward, especially for high power applications where you want it to fail safe. And one configuration that is being proposed is the recess gate GaN HEMT. Here you have to etch the AlGaN layer very accurately. It's a very thin layer, maybe 25 nanometers deep, down towards the gallium nitride where the surface has the 2-deg without damaging that surface in order to get the most out of your device. So there's various processes you can do. And then, so PCVD for the isolation, passivation, and then the gate recess can be done by atomic layer etching, which is a very new technology, very exciting technology, but also by a very controlled process. Then the gate dielectric, typically aluminium oxide, can be deposited using plasma-enhanced ALD. We found that plasma-enhanced ALD gives the brilliant material qualities, but also allows you to address the surface before you deposit. And this means you can reduce some of the defects on the device and create a much better device. I mentioned the effect of the pre-treatment of the surface. Basically, you're removing the gallium oxide native layer, and this is done through the plasma itself. And then, without breaking vacuum in the same process, you can just then deposit straight onto this improved surface with the ALD. Atomic layer deposition is a very, it is now a mature technology that allows you to deposit very accurately thin layers of very high quality dielectrics. To serve this market, the ALD market in high volume manufacturing, we've recently launched our Atom Fab tool. This is specifically designed for high volume manufacturing ALD performance. So we looked at our previous system, which had very, very good material qualities, very, very good device qualities, and then made it much faster. So there's some patented technology going into this solution, which allows you to deposit the ALD layers much, much faster, giving you the throughput and the cost of ownership that's definitely required as you move into production. So as a company, as this compound semiconductor industry is maturing, we're also maturing. So we're investing heavily in infrastructure and then also product development and personnel. We are recognizing that we can follow the market and make sure that we deliver what the high volume manufacturing companies require. So for example, we put a clean room test area where the systems go into for final test. Customers can come and visit, have a look around the tool, and this is a clean room environment before the tool is shipped out to the customer. So we're very aware that our customers are continuously developing. So we work very closely with them. We have a very strong installation base in the academic community, and we work very close with them to make sure the latest innovations that they are producing, we can help them get the most out of those with our systems. But then we follow them into, first of all, sort of pilot line production, then following that into full-on high-volume manufacturing. And we've done this many, many times over the years. This is something we're very comfortable doing. We're very happy to see our customers mature and take their great innovations and research fully all the way into high-volume manufacturing. And to do that, we have a suite of systems which are production ready. So they're with industry standard handlers. So you get the maximum throughput and lowest cost of ownership from our systems. So, in summary, Oxford Instruments plasma technology has been working in the compound semiconductor market for 40 years. We have a wealth of experience within the company. We know how to get the most out of the compound semiconductor devices. We are very active in speaking to the community. We work very closely with the community to understand their needs and to make sure that they understand what they can achieve through plasma processing. And we partner very closely with certain institutions to support the business growth. And we're very, very focused on the compound semiconductor industry. We're investing heavily, making sure that we have the correct infrastructure and the correct processes, solutions in place to make sure that we continue to deliver the best quality solutions to our customers. Thank you for listening. I hope you enjoyed it. Now we'll have some questions, please.
Thank you very much, Mark. We have a question which says, who are your main competitors in the ALD segment of the equipment business?
Oh, good question. Who are our main competitors? Well, I guess the typical ones, if anyone knows ALD, Benek, Picasson, people like that. But yeah, it's a strange question to ask a vendor, should we say.
Ah, okay. Thank you very much. That was from Gopal Prabhu. And I think we have, it's the same question, just a repeat from different areas. Is there any other questions for Mark? No? Or any of the speakers that you weren't able to catch up on? I know we have Gerald back with us. No, in that case, thank you very much, Mark. Very good. And see everyone in Brussels in November. It was running slightly ahead of time now, probably thanks to not so many questions, so feel free to make up for it. Oh, sorry, Mark, before you go, there is a question, do you see any other markets for gallium nitride? That's for Ilan Bonov. I think that may be for Gerald, actually.
Yeah, I think that was for a previous speaker.
Yeah.
Gallium nitride is a great material, so it's going to be used for, micro LEDs, for the RF switches. So it is very exciting.
Yeah, quite broad. Gerald, did you want to comment on that?
Yeah. So basically, in my talk, I presented mainly the server and telecom, but we do see also opportunities in chargers and adapters, and in markets like all-in-one PC and flat television. So whenever power density form factors are important, gallium nitride is offering a very good chance.
Okay, thank you very much. And I think that's it for all the questions. So thank you, Mark, and thanks, Gerald, for jumping back in. Okay. On that, we'll move on to the next presentation, which is from Samuel Sonderegger, who's the Chief Executive Officer at Atolite. Samuel's talk is the non-destructive dislocation and doping monitoring for gallium nitride hemp high-volume manufacturing. It's well known that dislocation density and type influence reliability and performance of a GaN high electron mobility transistor. Moreover, control of the dopant concentration and dopant activation are crucial to the reliable manufacture of high-performance gallium nitride HEMTs. Atolite will present a non-destructive, fab-ready, and inline-capable solution for monitoring these parameters. Samuel's presentation. Thank you.
Thank you, Mr. Chairman, for the kind introduction. Good afternoon, everybody. So today I would like to talk about our solutions for non-destructive dislocation and doping monitoring for gallium nitride HEMT high-volume manufacturing. Atolite is a company based in Switzerland that was actually already created back in 2008. Today, we supply and service a global customer base of key industry players and leading academic and research institutions with our innovative CL solutions that are being used today in process development, failure analysis, and also in research. We are the only integrated cathodoluminescence manufacturer in the world. This means today we're the only ones to provide this technology as a fully automated solution. We have been selling our FA and R&D tools since 2012, and we installed our first wafer tool back in 2018. So I think that we're all here convinced about the importance of gallium nitride HEMTs and their growing market. So I will let the specialized analysts in this session cover the aspect who will for sure do a much better job at this than me. So let me concentrate during this presentation on some technological aspects of gallium nitride HEMTs. And maybe let me first start with a very short technology refresher. So the inherently polar properties of three nitride compounds allows actually for modulation doping and at the same time for the formation of a natural two-dimensional electron gas at the hetero interfaces, which makes these materials ideal candidates for high electron mobility transistors. Of a very particular interest for gallium nitride HEMTs is actually the compound gallium nitride and aluminium gallium nitride, since at a specific aluminium concentration these two can be lattice matched in the C plane. And thanks to the polarization field of opposite signs of these two materials, we do have a polarization discontinuity at the interface, which yields to the natural formation of a two-dimensional electron gas, which can be used as the channel in a transistor. Now we have two types of transistors actually, the so-called depletion mode transistors. So these are normally on devices that are actually high performance devices that have been demonstrated quite some time ago and are already used today. However, what is actually needed most of the time is so-called enhancement mode devices, or a device that that operates in enhancement mode, which is a normally off mode, and this for obvious reasons like safety. One of the most important ones, safety for high current applications. In order actually to build a normally off gallium nitride HEMT, we need to add some additional layer to the stack we have shown before, so that the Fermi level can actually be pinned at the right energy to create a normally off or an empty channel when actually no voltage is applied to the device. So typically this is achieved by the addition of a p-doped gallium nitride top layer. And this p-GaN top layer needs to be controlled in a very careful way if we want to avoid any type of performance and reliability issues. So let's have a quick look at the typical factors that actually limit today the mass commercialization of enhancement mode gallium nitride HEMTs. So the first factor is the gate quality. That's what we just said before. So it's the quality of this p-doped gallium nitride. And what we need to control here is the magnesium concentration. This directly influences the threshold voltage of the device, its rectifying performance, and the source drain leakage. Then there's also a second aspect, another aspect, which is actually the active dopant concentration. So when magnesium is implanted in gallium nitride, what we actually want, what we're interested in, is by the fact of having the magnesium atom act as an active acceptor. So in the end, we're actually interested in getting the active magnesium concentration. The second factor is channel quality. So this is very much influenced by a carbon incorporation in carbon compensated GaN. This influences the device series resistance, but also the switching speed. Then the third point is robustness. So today, a big part of robustness actually comes back to trend dislocations, dislocation density and type. So first of all, we know today from literature that dislocations may contribute may or may not contribute to leakage current, depending actually on their type. And we also know from literature that actually trend dislocation density and type is involved in magnesium diffusion from the gate into the channel, which over time or during device operation will actually influence the robustness and also change the device series resistance. So let's see on the next slide which ones of these factors we can actually control with our solution. So first of all, the magnesium. So we have actually a very good evidence that by using our catalytic technology, we can measure a representative metric for the magnesium concentration by looking at the emitted light under electron beam irradiation. Now this needs very careful calibration. So the metric has to be calibrated for a given process during process development. And what we also see is that actually having electrons here has a very big advantage, because it seems that from when we try to do the same thing with photoluminescence, we do get a very strong background signal from underlying layer that actually washes out the signal we really want to observe. Then what is the link, or what is the supposed link between trend dislocations and robustness? So this here is a research paper that was published last year. What we actually see on top is a cross-section of a low trend dislocation density region. What we see in the figure below on the right-hand side is the same figure in a high trend dislocation density region. And we very clearly see a magnesium-related signal that indicates actually diffusion along trend dislocations when we have a high density of trend dislocations. So this in turn directly means that we actually have to control the dislocation density together with the magnesium concentration in order to get an understanding of how magnesium diffuses actually from the gate into the channel, and hopefully to avoid this type of effects. So what we can do with our technology is, of course, looking directly at trend dislocation density in a non-destructive way. So we see here a wafer map with a number of zones that were chosen to do high-resolution measurements. So in each of these zones that are shown here, illustrated here on the wafer, we get the high-resolution map you see on the right-hand side. And in each one of these maps, we do a very high-resolution trend dislocation density counting. What we can get them from this is either we get a wafer distribution, so we can plot this, interpolate this and get a full wafer map. But we can, of course, also just look into the high resolution map itself and try to find for some specific, try to find a specific faulty location. The next is the dislocation type. We have actually a very good evidence or initial results that tells us that catalytic signal allows to determine the trend dislocation type. And we know from literature, so this is the paper cited below from 2018, that only some dislocation types actually contribute to leakage current in gallium nitride. So we think it is actually crucial, even in a production environment, to be able to measure not just the dislocation density, but also the dislocation type distribution. So this is very early work that we are just about, we have just published. So this measurement has been demonstrated on the manual system, and development on the fully automated system is ongoing. So then what is this NT300, which is our fully automated catalytic tool? So we think today it's the sharpest tool in your statistical process control toolbox. So it is an automated 300 millimeter capable CL tool for pre-front-end verification of epi quality and statistical process control. It does have a cassette-to-cassette handling for inline metrology inspection, but it can also it also exists in a manual version with a manual wafer loading without the cassette-to-cassette set handling. So what we get from this tool is a drastically reduced feedback cycle time compared to SIMS for doping control, so down to 1 hour, whereas in SIMS it typically may be days, and also a drastically reduced measurement time for direct defect metrology as compared to XRE. With this, we support manufacturing cost reduction by reducing WIP, and we accelerate development speed. And of course, we do give you a non-destructive wafer scale uniformity feedback. So let's have just a very quick look at the reproducibility of this measurement center tool. So here we show results of a simplified gauge R&R exercise. So we look at the variation of a parameter A, which here happens to be energy, so recombination energy, which has to be measured very, very carefully in order to do all the analysis we need to do. So we have measured this over 3 different locations, over 4 different days. And actually, we see a day-to-day variation that is maximum 0.019%. Now, to put this a little bit in perspective, this means a wavelength resolution that is better than an angstrom, which is actually extremely, extremely good. So with this, I'm already at the end of my presentation, already 10 minutes. So thank you very much for your kind attention. And I guess the floor is open for questions.
Absolutely. Thank you very much. So are there any questions for Samuel? I think we have one hand raised, so that's from Eric Don. And you're being unmuted, so you should be able to speak. Hello, Eric? No. We've lost the question. Okay, that's fine. Perhaps Eric will come back. So thank you for that, Samuel. Just checking if there's any other questions. No, I think we're fine for now. So thank you very much for that, Samuel. Very good.
Thank you very much.
I
will still be around in case there are some questions later. Thanks.
Excellent. There's sometimes a bit of a lag coming through, so we'll save those up for you. Thank you very much. Okay, in that case, I'll move on to the next presentation, which is from Dr. Wynne Meredith, Director of the Compound Semiconductor Center and also of CS Connected. Over the last few years, there has been a growing cluster of compound semiconductor activity in the South Wales valleys, and long-term and long-established industry players such as IQE, Newport Wafer Fab, SPTS, KLA, and Microchip have been the catalyst for significant supporting infrastructure in research, development, and innovation to form what is now emerging as a new Silicon Valley with a focus on compound semiconductor technologies. Dr. Wynne Meredith will provide a high-level overview of the emerging compound semiconductor cluster, CS Connected, with an example of the role that the cluster can play in areas such as power electronics. So if we can kick off Wynne's presentation.
Hi, my name is Wynne Meredith, and I'm here to talk to you about seeding a technology cluster in advanced semiconductors in South Wales in the UK. My agenda for the next 10 minutes is just to give you a very high-level view of the rationale for Compound Semiconductor Connected, or CS Connected, highlight our current footprint in the South Wales region in the UK, detail some of our strategic investments to date, and link to power semiconductor activity, which is the theme for the current session. If we look at the history of the development of silicon semiconductors in Europe, it's been dominated by a cluster model with 4 clusters of excellence around Grenoble, Eindhoven, Leuven, and Dresden. Analysing these clusters highlights there are typically over 800 companies, over 150,000 jobs, and activities in these clusters secure the majority of all research and development and innovation funding in Horizon 2020 around semiconductor development. Our vision is to create Europe's 5th semiconductor cluster, the world's first compound semiconductor cluster in the UK, in the region of South Wales. In terms of the footprint we already have in the region, CS Connected is a formal collaboration of 10 partners. 4 companies, IQE, Newport Wafer Fab, Microchip Corp, and SPTS. 2 universities in Cardiff and Swansea University, and research technology organisations such as the Compound Semiconductor Centre, which is a joint venture between IQE and Cardiff University, and UK's Compound Semiconductor Applications Catapult, which focuses on innovation in the semiconductor application space. We have a 600 million investment runway at the moment since the vision of the cluster was launched in 2016. Currently, we have a wide range of investments ranging from large-scale capital investments on university campus at Swansea, the new Centre for Integrated Semiconductor Materials, and Cardiff, the new Institute for Compound Semiconductors, through to large-scale operational research projects, through to large-scale investments in manufacturing infrastructure, such as a 40 million investment in a new epitaxial materials manufacturing plant in Newport. The current headcount of the cluster sits at just under 1,500 direct employees in research and development, engineering, and semiconductor manufacturing. And our economic model suggests that that leads to an indirect headcount of around about 760, so a total of just over 2,200 employees, which has a net gross value add to the region of 180 million per annum. The vision and target for the cluster is to double those numbers by 2025, to move towards nearly 5,000 jobs in the region, with a contribution of upwards of 380 million per annum. If we deploy these assets towards power semiconductor markets, we have an ecosystem initiative in place which combines our research, development and innovation elements in materials, fabrication, packaging and applications, along with a coordinated foundry supply chain with wafer level materials provided by IQE, wafer and component level fabrication with Newport Wafer Fab, back-end packaging and test supplied by Microchip. Currently, we're considering a roadmap which focuses on gallium nitride now as the capability is in place, looking at a 2-year horizon for silicon carbide capability and a 5 to 10 year horizon for next generation power materials such as gallium oxide and high aluminium content argon. In terms of phase 1 of that plan, deploying pilot line and analytical capability, this will be focused at the region's universities, both Swansea and Cardiff. As mentioned, the Centre for Integrated Semiconductor Materials is a 90 mil project with a £30 million capital build, which is currently underway and due for completion in March 2022. It will provide a manufacturing grade research and development fab for a wide range of integrated semiconductor and functional materials. At Cardiff University, we have a £75 million investment in a new translational research facility that will house the Institute for Compound Semiconductors. This is about 130,000 square foot research hub, which will contain a 6 and 8 inch wafer device fabrication line for compound semiconductor devices. This is due for completion in Q4 2021 and open its doors within 6 months after that. In terms of phase 2, scale up to volume, we have several sites available for expansion. As mentioned, IQE has already invested 40 million in a site in Imperial Park in Newport and deployed 10 epitaxy reactors in a facility which is 360,000 square foot and has capacity for 96 reactors. This is already the world's most sophisticated compound semiconductor manufacturing plant, and it's complementary to additional capacity at St. Mellons, IQE headquarters, where there are already another 15 MOCVD reactors, including 2 dedicated to gallium nitride power materials. This will be the largest of 9 global manufacturing sites, 4 in the US, 3 in the UK, 1 in Taiwan and 1 in Singapore, and complements an existing investment in gallium nitride capacity in place in IQE US. In terms of fabrication, in Newport Wafer Fab, we have the UK's largest semiconductor manufacturing centre. It was formed 2 years ago as a management buyout from Infineon, although the site has been active for at least 30 years in terms of development, advanced power device development and manufacture. Management team are currently working towards compound on silicon foundry model with an open access foundry business model that is automotive and medical qualified. The current capacity is about 8,000 8-inch wafer starts per week, but the facility has 28 acres of land for expansion, which is expandable to 14,000 wafer starts within the building envelope. So the takeaways of today's introduction: compound semiconductor front-end market is worth about 4 million wafers a year by 2023. The global power market is expected to be 10 to 15% of that, but high growth at 30% compound annual growth rates. CS Connected, as a regional cluster entity, is gearing up for growth to address this market. We already have 250 million investment commitments across a wide technology readiness level ecosystem already in progress. There's clear potential for power electronics wafer to package capability in the region to leverage off the existing 1 billion sunk capital and planned future investments. Power Wales is an early stage plan to leverage such assets into power compound semiconductor markets, and we currently have supporters from all over the UK, and we welcome discussions with new EU partners. Thank you very much for your attention.
Okay, thank you very much, Wyn Meredith, for that presentation. I'm happy to field any questions that there may be on that as I work alongside Wyn very closely with CS Connected, which is the umbrella organization for the emerging cluster in largely around South Wales. It is a unique structure, if you like. It's a combination of everything from TRL 1 through to TRL 9 from the universities through to high volume manufacturing, with support from a number of government agencies, and in particular the Welsh Government and the Cardiff Capital Region. So if there are any questions, if you'd like to raise your hands, your virtual hands, or just type it into the chat box, I will be happy to field those or defer to Wyn. Okay, I don't think there are. We're actually running about 15 minutes ahead of schedule. Normally, when we have our conferences, we're able to manage tea breaks and so on to be able to make up or lose some time, but we don't have that facility. But if you'd like to switch a kettle on, that's fine. I will move on though to the next presentation, which, although we're slightly ahead, I think Eric is with us, and Eric Hyam is Director for the Gallium Arsenide and Compound Semiconductor Technology Service at Strategy Analytics. This will be the first of the final 2 presentations, both of which give market overviews. And Eric will be assessing the impact of 5G front ends on the world's leading gallium arsenide fabs. As 5G networks and devices deployment increase, the electronics industry is realizing that this is both a blessing and a curse. The blessing is that these new applications will increase quantities at a time when the market is flattening. The curse is that the backhaul requirements create more optical backhaul and transport opportunities. This presentation explores drivers and trends for data traffic and the impact of gallium arsenide content in front ends. It will also address the gallium arsenide opportunities in fiber transport applications and assess the gallium arsenide foundry capabilities in this supply chain versus the pure play radio frequency gallium arsenide foundries. So let's hear from Eric.
Hello, everyone. I'm Eric Hyam with Strategy Analytics, and I'd like to spend the next 10 minutes or so talking about 5G and its impact on the gas industry. Here's what we'll talk about. A couple of quick slides about Strategy Analytics as sort of a credential check. Next, I'll touch base with the 5G vision, because that's really going to be the driver for the gas industry going forward. We'll take a quick look at the backhaul market, because I think there will be some interesting challenges and opportunities for gas. But at the end of the day, the cellular market determines the overall trajectory for gas. So we'll dive into that in a bit more detail. Then I'll wrap up everything. So these are some of the important issues that Strategy Analytics is looking at across the entire commercial and defense supply chain. Data traffic is really the driver for the entire electronics industry, and we're working with clients to understand the best technologies and architecture for the supply chain and how these translate to semiconductor requirements. I won't get into this slide in too much detail, but in our semiconductor and component services, we're working from procurement dollars, whether that's defense budgets or operator CapEx spending, all the way down to starting material and equipment for a variety of compound semiconductors and RF silicon technologies, really in all the commercial and defense applications. And in these areas, we're developing models, identifying trends and drivers, all of the research items you've come to know and love. So let's take a look at 5G. By now, I'm sure we've all seen one of these three-pronged 5G diagrams. I like this particular graphic because it shows the three pillars of 5G at the corners of the triangle, along with some of the performance goals around the perimeter. But at the end of the day, the 5G vision is really about faster speeds, lower latency, and more connections. So how do we implement this vision? This is another graphic that I like because it shows a lot of the features and implementations that 5G has to address. On the right side of the slide, I've listed some of the network enablers that the industry has to address. MIMO antennas and beamforming, along with pushing more intelligence and capabilities towards the edge, will be central to this 5G vision. Well, by now we've probably all seen the Cisco data traffic estimates. And to understand the challenge of 5G, I said, let's look out into the future. We're 10 years into the 5G era, and what does it look like? Well, fortunately, the curve fits and extrapolates nicely, and the answer is data traffic growth to this point has been fast, but it's going to get even faster, almost 30 times faster. So let's take a look at the backhaul market now. So how are we going to get to this 30x increase in data? I mentioned earlier that massive MIMO antennas are going to be fundamental enablers of 5G. The chart in the lower left shows that a MIMO antenna with 64 radiators using 100 megahertz channel bandwidth generates 313.6 gigabits per second of data traffic from each antenna. And we're there already for some millimeter wave networks. The chart in the upper right takes that calculation a step further. It shows that with 256 antenna ports and 1 gigahertz channel bandwidths, so we're not quite at that point just yet, but we're headed in that direction. And when we get there, that antenna is going to generate about 13 terabits of data traffic. So that's the challenge to the wireless community. An even more rapid increase of 5G data traffic. However, this success could be a curse to the wireless industry. So what do I mean by that? Well, this slide shows Ericsson's estimate for the mix of backhaul technologies, and it's pretty interesting. They try to put a positive spin on the wireless share, pointing out that 65% of the market will be wireless in 2023. That only begrudgingly admits that if Asia is included, that percentage drops to 40%, and it's decreased over time. So that's the challenge. Declining market share brought about by fiber backhaul in response to large increases in data traffic. The vision for future backhaul networks is that they're going to be a hybrid of frequencies and technologies as shown in this diagram. So here we see a mix of microwave and millimeter wave frequencies and architectures configured to provide the best solution for the traffic demands, and not shown, but stitching everything together as fiber. So we've talked about the curse, but now let's talk about the blessing. While the backhaul architecture question is an interesting one, and it's a good market for gas, at the end of the day, nothing moves the needle of gas revenue like the cellular market. As this chart shows, the cellular portion accounts for more than half of gas revenue. If we look at the historical performance of the gas market, the early days were defined by defense funding and applications, but since about 2004, the driver has been cellular, and that's what's pushed gas revenue to historical highs. specifically, this driver has been smartphones with their increased RF content. As the chart shows, the big ramp of smartphones is really what drove the industry to rapid growth in the mid-2000s. But we can see a definite flattening of growth around 2016 and even a drop in market share through last year. And this is what ultimately led to a decline in 2019 gas revenue. Now, I should mention that this forecast is pre-COVID-19, but the trends will stay the same. 5G will become the new growth driver for the gas industry, but it's looking like COVID-19 is going to forestall that recovery a bit. So there's some interesting nuts and bolts going on with 5G, and this is an eye chart, but intentionally so, to show both the challenge and the opportunity. On the left is a table of 3GPP approved 5G frequencies, and you see there are many. The graphs on the right show that there is some sub-6 and millimeter wave harmonization. You see some of the regional activity. So you see harmonization around 3.5 gigahertz and 28 gigahertz, but definitely lots of activity. So as I mentioned, this is both a challenge and an opportunity. This chart summarizes activity. And first of all, there's a lot of nomenclature. Low, mid, and high band, FR1, FR2, sub-6 gigahertz millimeter wave, but they all point to the need for more bands, higher frequency coverage, wider bandwidths, and things that point to more RF content, and that's typically been good for gas. Okay, so lots of bands, millimeter wave content, more radios. What does that mean? Well, it means an enormous RF opportunity. Again, another eye chart, but when you get a chance to review this slide, look at all the channels, bands, and radios. That's the opportunity for the semiconductor market in general and the gas market specifically. So this is a recent forecast, again, pre-COVID-19, and we see the growing importance of 5G in the cellular market. More bands, more performance, more RF. Another pre-COVID-19 forecast that has gas revenue surpassing $9 billion in 2024. I'm in the middle of making a best guess at the effects of the virus, so stay tuned for that. But I think the demand fundamentals remain strong. So we'll get there, but things are likely to be delayed a bit. And it's also interesting to note that gas foundry revenue runs about 10% of OEM revenue. So that's a healthy segment that I expect will continue to grow. So let's wrap this up. I pointed out that data traffic, the devices that enable it, and the networks that support it are the growth engine for gas revenue to this point. Slowing smartphone growth has provided a big headwind for the industry, ultimately leading to a revenue decline in 2019. But 5G is poised to be the new growth engine for gas. Now, COVID-19 is going to change the timescale for this growth by delaying the eventual ramp of 5G. But again, we'll get there. So stay tuned for more comments on the COVID-19 situation because it's very dynamic. And since I'm out of time, I won't discuss this slide, but if I've raised some questions, please feel free to contact me, and I'd love to discuss some of the ways we can help you answer those questions. So aside from that, thanks to the AngelTech communications team for enabling this, and thanks for your time.
Thank you, Eric. And Eric is with us if there are any questions from the delegates. Again, raising a hand to ask a physical question, and I can see one hand raised. Akinori Ubakata. And you should be muted so that you can speak.
Yes, hello. My question is, could you comment about the any kind of the material for the 5G network? Because the some of people use the silicon gallium, and some people thinking about the indium gallium phosphide. So why do you talk about only the gallium arsenide?
Yes, thank you for your question. The presentation focused specifically on gallium arsenide, but you bring up a good point, and I didn't get into a lot of detail on the 5G base stations in particular, but that's really an area that is a technology battlefield right now, because you mentioned silicon germanium. What we've heard is that a lot of the millimeter wave, especially massive MIMO antennas that are rolling out with silicon germanium. That might not be the best long-term technology. Gallium nitride will figure prominently, as will silicon, in 5G. And if you speak to any proponent of that particular technology, they'll give you a lot of compelling reasons why that's the best technology. Gallium arsenide will come along as a willing participant with gallium nitride. In most cases, we talk about a gallium nitride power amplifier, but that typically includes gallium arsenide driver. You know, other compound semiconductor technologies, indium phosphide, silicon germanium, again, have a lot of exciting opportunities in optical markets and other markets. So great question, thank you. But this presentation was specifically focused on gallium arsenide and 5G front ends. So thanks.
Yes, thank you, Akinori. I have a question for you, Eric. You covered the COVID situation very well. We've also heard lots of rumors about COVID encouraging people to go online and using things like Zoom, as we are now, and WebEx and other facilities are available, of course, but also that it may change working habits and actually to the detriment of other services such as transportation and so on. We may find a lot more working at home and a lot more reliance on such systems, which in turn should drive 5G. Do you have any thoughts on that? Because there are conflicting arguments.
Yeah, that's a great question, and one of those unknown at this point, but it's been interesting. I mentioned when I put the presentation together that I was monitoring it. I fairly recently published an insight, and the information that I could dig up really supported what you just said, that anything related to bandwidth, whether that's network or devices, you know, we're all working at home, we all rely on high bandwidth internet connections. So anything related to that, everyone is ordering online now. So anything related to data centers, any of the interconnects, be they optical or, you know, silicon photonics, any of those, medical is another one that is actually seeing a big jump in demand. Now, again, if I focus just on the gallium arsenide and to a larger extent the total compound semi market, that's so linked to handsets that, you know, we all tend to look at those handset projections and they're down 15% to 20%, but that's moving up and down. So that tends to drive an overall a bit sour outlook, but there are definitely markets or segments within the market, subsegments, where we're seeing demand pick up. So it's, you know, it's an interesting challenge.
Absolutely. Thank you very much for that. Thanks, Eric of Strategy Analytics, and I guess we'll see you too in November, hopefully in Brussels. Right, and our final presentation today, just checking there's no more questions for you, Eric. No, that's great, thank you very much. Our final presentation for today is from Claire. Claire Drodek is Director of the Power and Wireless Division at Yale Development. And it's about 5G's impact on RF front end from telecom infrastructure to handsets. So following on the same theme. The telecom infrastructure market has not moved much in the past decade in terms of the value of operators' investments, but customer pricing also keeps decreasing, and building new infrastructure keeps showing smaller and smaller returns on investments for telecom operators. In this context, an attempt to create new markets and enlarge operators' reach to customers beyond handsets created 5G. The global landscape at network level will now move much before, will not move much before 2025, but it will definitely change in terms of the technology and antenna systems, thus completely restructuring the radio frequency component industry. At handset level, the main phone manufacturers differentiate from each other on the RF field by adopting either an integrated or a discrete approach. The market leaders, Samsung, Apple, as well as smaller OEMs such as Sony, LG, Google, or ZTE, are moving towards integration using complex RF modules from Broadcom, Skyworks, Qorvo, Qualcomm, and Murata. Whilst the market challengers, Huawei, Xiaomi, Oppo, and Vivo, which drive as much volume as the market leaders, differentiate by favoring a discrete approach whenever possible. In this presentation, Claire will review how 5G is reshaping the RF front-end industry. She will explain the positioning of the main component and module suppliers and review the technology mix needed to support 5G. So over to you, Claire.
Welcome everyone. So my name is Claire Troidec. I'm heading the Power and Wireless Division at Yole Development, and I will guide you through the presentation of today, 5G impact on RF front-end from telecom infrastructure to handsets. So if we start with the telecom infrastructure, the idea is really to look at the deployment of the 5G infrastructure from region to region. So what we see here in this schematic is the sub-6 microsites are interesting for Europe, US, Japan, Korea. China is heavily investing into this. They have good coverage with a lot of bandwidth from their telecom operators, such as China Mobile, for example, and China Telecom. If we look on the millimeter wave aspect, so it's being pushed by US and Japan, Korea, not for the same reasons. In fact, in the US, they're looking for coverage, while in Asia, it's mainly for the dense urban areas where you would need this technology deployment. If you look at the rest of the world, we'll see that it will still take time. In India, the other countries, the deployment is not expected before 2023, for example. So if we look now at the evolution of this different base station, you will see in fact that LTE 4G brought remote radio heads, and 5G brings active antenna systems. So what does it mean? It means that the main changes this induces is that the remote radiohead systems, they are based on a few high-power RF chain to send the signals, whereas the active antenna systems, they use up to 64 independent low-power RF chains. So this will multiply the number of RF components and add some new technologies such as beamformers and creates a market for low-power RF power amplifiers. So if we look today at this market in terms of volume, if we look at the antenna systems, these base stations, so today around 2020, we have a bit more than 2 million units deployed worldwide. Of course, there's a split in terms of technology. So most of the market is composed of remote radiohead-based antenna systems, here depicted in orange, for example, for 4G. And this market in the future will be cannibalized by 5G active antenna systems and 5G small cells. You could see these small cells as active antenna systems with a lower power outputs, so destined to dense urban areas and smaller structure for short-range, high-throughput transmission. So some active antenna system will also appear in 4G deployments to improve the LTE throughput in urban areas, and remote radiohead and active antenna systems will coexist in the future and will be complementary. Of course, now these major changes drives a lot of interest today from the component makers in this domain, where cards are being shuffled. If you look at the various areas, so you will see players in the digital front-end, analog front-end area, players in the RF components, players in the base station. So of course, in terms of OEM integration, it's mainly dominated by 5 big players, the Huawei, Samsung, ZTE, Ericsson, and Nokia. But we will see that there are really a lot of other companies involved either at backhaul or for small cells. And in fact, this market is highly complex, highly competitive, and not yet consolidated at the moment. So if we look overall at the market in terms of value, today in 2018, it was around $1.4 billion, meant to grow to $2.5 billion with an 8% dynamic growth. The biggest part of this market is being taken by the power amplifiers. So in fact, you have a first amplification with a gain block to reach the RF board, then a 3-stages amplification with the pre-driver, the driver, and the final stage PA. It's performed before reaching the antenna. So the high growth really are for these different PA markets. And we will also see, for example, the difference between the final stage PA, the gain block, for example, and the pre-driver and driver. You'll have other pockets of high growth, such as switches, for example, and the beamformers as well. Okay, so now if we look in terms of wafers, so we made the exercise to go down to the number of components needed in this base station and looking at the die size, how much does it represent given the different semiconductor technologies we have. So overall, the wafer starts, they will see a growth similar to the market growth. Okay, so we are in an expansion phase before it will be plateauing due to the limited investment, in fact, from the telecom operators. But due to a combination of die size, downscaling, and integration of multiple functions in this MMIC, the silicon-based technology will record a modest growth in the next several years, despite a volume increase in terms of component number. Otherwise, you will find in yellow the compound semiconductor platform. They will increase in wafer start volume as the downsizing and the wafer size transition are limited. So gas will remain a substrate of choice as it is often used by default by the RF designers as it provides the right performance level at the market for which no failure is in fact allowed. Now let's look at the handsets. For the handsets, of course, we've seen from generation to generation an increase in terms of RF content, moving with the implementation of diversity path, more bands being implemented, carrier aggregation, dual connectivity. Now we are talking about millimeter wave antenna in package. So definitely the RF content is increasing. If we will look at different smartphone and what does it represent in terms of bill of material expressed here in squared millimeters, so in areas. So we took various phones from entry level to mid-end to high-end levels that we looked at thanks to a System Plus providing tear down and cost analysis. What we will see is that the integration choices, they really depend on the OEM. They are very different from one company to the other and from one model to the other. What we do see is the Huawei bill of material really increased strongly since the Mate 20 that you will see here with 66 squared millimeter for the RF front end. Since then, for the 5G version, a lot of bands have been included, 4x4 MIMO with discrete implementation compared to modules. So we do see that the 5G implementation definitely increases the bill of material for the various phones. And here the 5G phones we are showing here are the sub-6 gigahertz phones. So overall, if we will express this market in value, so moving from a $15 billion market in 2018 to a $25 billion market in 2025, the volume in terms of compound growth will be around 8% in these coming years. And what you do see is that power amplifiers is, of course, a big take for this overall market. But multiplexes, filters, duplexes, diplexes components, they represent the largest volume, and they will double from 2018 to 2025, reaching more than 100 billion units to support the 5G new radio bands filtering, routing, and carrier aggregation. 5G will also boost the need for the LNA to comply with 4x4 MIMO download requirements, either in discrete configuration or in modules. And also LNA switch components will gain momentum over separate LNA and switch configuration for better integration in compact diversity front-end modules. So if you would do the same exercise and express this market in terms of wafer volume, you would see here that's what we've depicted here, the lithium tantalate, lithium niobate. So that's the market for the SAW devices that will see a moderate growth because most of the volume increase will be taken by the transition from 5-inch to 6-inch wafers. And the high growth you will see for the silicon-based wafers, so either a 6-inch or 8-inch, and silicon in fact aggregates all the following functions: filter, switches, tuner, LNA, PA. And the filter, in fact, mostly explain this growth envisaged for the silicon wafers with high filtering functions such as F-bar, so bulk acoustic resonator, and IHP SAW-based devices. We could also say a few words on the SOI-based platform with 12-inch wafer starts that will grow due to the implementation of 4x4 MIMO on the 5G new radio, which will lead to an increase of LNA and LNA switch devices. And the 6-inch gas also, they will grow slightly, and in-gap HBT will remain the main technology for the high-power PA. So all these slides were extracted from various reports we have on this area, thanks to YOL and System Plus. And I thank you for your attention, and I'm looking forward to the Q&A session and the more face-to-face speech that will be held towards the end of the year. Thank you for your attention.
Thank you very much, Claire. Very interesting. I'll ask again if there are any questions to please raise your virtual hand by clicking on the option in the Zoom panel or by typing it into the chat box. Getting to the end of a very long session. I think if this was live in Brussels, I'd be asking the caterers to put the fries on and get the mayonnaise ready, but we'll look forward to that in November. Okay, in that case, thank you very much, Claire. No questions? In that case, all it leaves me to say is thank you to the organisers, AngelTech, for pulling everything together. We've actually had, I know it was somewhere in the region approaching 1,000 registered delegates, and seeing people popping in and out. We've averaged about 100, I think, at any given time in this particular room. So I hope everyone's enjoyed the session and the speeches. I'd like to thank all of the speakers for their contributions. Very interesting half a day. And also special thanks to our partners, our sponsors. The Platinum partners are Atolite, CS Connected, EVG, Ferrotech, Oxford Instruments, Taiyo Nippo Sanson, and YOL Development. And our gold partners were Semiconductor Services Inc., Evertech, Intivac, and IQE. So thank you very much to the sponsors. All of the sponsors and speakers do have rooms that are effectively accessible, so you can access them after this event, either right now or for the next 6 months, pretty much leading up until we have the event in November, which will be held in Brussels on the 17th, that's Tuesday the 17th, and Wednesday the 18th of November, all being well. And that will be the 10th CS International, and it will be accompanied by the other conferences, which is PIC International, the SSI, and the Sensors Conference, and we look forward to seeing you there. If there are any final questions for any of the speakers, please could you raise a hand now. I have one question, which is, will the recordings be posted? My understanding is yes, they will be available along with the access to the virtual exhibition rooms, and that will be accessible through the CS International website. In that case, if there are no more questions for any of the speakers, and I think most of the speakers are still online, I will thank you all again for attending. I think it's been an interesting session in these interesting times, and I think just the volume of visitors and delegates that we've had online throughout the afternoon shows that it's actually a pretty successful way of doing things. So may it long drive the demand for 5G connectivity and all of the other activities that compound semiconductors are involved in. Thank you again. And look forward to seeing you in November in Brussels. Thank you.
Thank you very much. Bye.
Thank you.